Yeah, maybe we can start. What do you say, Professor Kuze? Should we start?
Yes, I think so.
Yeah, okay. Okay, maybe Professor Subhash, you can go ahead.
Yeah. So, good morning, all of you. Today, there are two presentations by Professor Hirahara and Professor Uday Narayan Maiti. Let's welcome Professor Hirahara, who is going to talk on quantum properties of atomic layer films, topology, and superconductivity.
Okay.
So,
Thank you very much for the introduction. So I also thank the organizers for this wonderful workshop. And I am Toru Hirahara from TokyoTech. So today I'd like to introduce our recent results concerning these atomic layer films. And hopefully the number of audience will increase as I proceed. Okay. So before going into the details, let me just give a brief introduction to what we do. So we are experimental group in condensed matter physics, and we are particularly interested in very thin materials. So first thing we need to do is we need to make a very nice film based on surface science techniques with atomic precision, meaning it is clean in the atomic level. So to do this, we characterize the structure with electron diffraction or a scanning tunneling microscope, as shown here. And then after we are sure that we have made a very clean system, we do further characteristics using angle resolved photo emission, which can measure the electronic properties of a material. And also we do transport measurements using a very special technique as shown here. Recently, we are very interested in also magnetic properties. So for this purpose, we use a magnetic circular dichroism or squid measurements. And we also have a big collaboration with theorists also. So with these measurements, we try to get new physics. And especially today, I will talk about the superconductivity and topology business. But this also can go the other way, as shown here. So sometimes theorists say certain new materials can have very interesting characteristics. So we have a lot of discussions with theorists and try to make the new materials that they predict. So we continue this cycle and make new materials and try to get the new physics out of it. So this is the overview of what of the research in our group. So particularly today, I would like to talk about high temperature superconductivity. And secondly, I would like to talk about magnetic topological insulators as shown here. So first, this superconductivity. So nowadays, it is possible to make very nice, high quality ultra-thin materials. And we are able to investigate if they are superconducting or not. So in the first material we studied, we made a bilayer indium film on a silicon substrate and measured the superconductivity. So this was achieved at temperature like 2.7 Kelvin. And then we continue to do other systems. So this is another material which we used silicon carbide as a substrate. And first we made graphene on silicon carbide, and then we intercalated calcium atoms inside the bilayer graphene. And this also became superconducting around like 4 Kelvin. And furthermore, we also can use the graphene as the substrate and grow chalcogenide films, such as niobium diselenide as shown here. And this also became superconducting at around 1.5 Kelvin. And you may notice that all of these materials are superconductors, but the TC is very low. This is natural because basically when you make a superconductor thin, the TC should decrease or it doesn't become superconducting. So this is quite natural. But if you look into the literature, there's one system that doesn't follow this common sense. So this is iron selenide. In the bulk iron selenide, the TC is like 8 Kelvin. But if you make 1 unit cell thick film, which is 3 layers of selenium, iron, and selenium on strontium titanate, as shown here, the TC is enhanced to like 100 Kelvin at the most, and in this work, it was like 40 Kelvin. So in this system, something strange is happening, and the TC is enhanced by making the film thin. And so what is important in this system is that there is something strange happening at this interface. So this can be understood if you look into this work, which is the first work that showed the high temperature superconductivity. So this shows the density of state mapping as a function of energy. And this is the Fermi energy measured with an STS, scanning tunneling spectroscopy. In the 1 unit cell film, you find this gap, which is a superconducting gap with these quasi-particle peaks. So this is a superconductor with a large superconducting gap. But if you make another layer on top of it, it doesn't show this superconducting gap. So this data alone shows that this 1 unit cell system is very special. And another example is that if you make the same film on a different substrate, namely graphene, what you find in this system is the usual behavior that the superconducting transition temperature here decreases when you make the films thinner and thinner. So these two examples really show that this 1 unit cell iron selenide film on the STO surface is very special system. But if you take a close look, something is a bit strange. That is what the TC reported in different reports is very different. So for example, in this work, they use angle resolved photon emission. And this is the superconducting gap here with the quasi-particle peaks here. But by raising the temperature, they try to determine the TC when this gap structure vanishes. And in this work, it is concluded that the TC is around 60 Kelvin. While in the very first work, this is the superconducting gap measured with a scanning tunneling microscope. The TC was reported as 40 Kelvin. And as I already showed, transport measurements show very different TC, even though we think everybody is discussing the monolayer iron selenide on the STO surface. So to summarize what I have just said, the monolayer iron selenide on STO surface substrate shows a high TC, and this is probably due to some interaction from the substrate to this film, such as some electron doping or electron phonon interaction effects, or something else as shown here. So if you take a close look at this interface, there is something which is this STO surface. So this STO surface should have a great impact on what this substrate is influencing to this film. But if you take a close look, you notice that although there are many different STO surfaces, very little care is taken about which surface to use in the first place before growing the film. So this may be the origin of the scattering in the reported TC. And just to give you an idea of how different this STO surface can be, this work reports STO surface. And this is heated up in ultra high vacuum conditions to clean the surface in the atomic level. But you can see that the color of the sample is totally different. And by electron diffraction, you can determine the surface periodicity. And this part shows what is called a √13 structure, which means that the periodicity at the surface is √13 times larger than the periodicity at the surface. And in this part, it is 2 by 1. This part is √5 by √5. So this example really shows that you need to be really careful about what kind of surface you're using as the substrate. So in this study, in this project, what we want to clarify is how different can the superconducting property of this monolayer iron selenide film can be different depending on the different STO surface we use. And if we can get some knowledge about this, I think it will be possible to control that. It is now possible to control the superconducting properties, and then we can find the optimum condition to get the highest TC for this system. And the ultimate goal is to establish. So until here, this is very material specific, but can we really make a general rule to realize high temperature superconductor in atomic layer systems? So this is the motivation to do this kind of study. So now let me explain about the experiments. And the most important part of this study is how to get different STO surfaces. But this is a bit technical and not so interesting to many of you, so I will skip the details. But what you do is you buy an STO substrate and you put it in ultra high vacuum conditions. And then you try to heat it to get rid of the contamination at the surface. And by doing that, you will get some periodicity. And to get some other surfaces, you need to anneal in oxygen atmosphere, because if you anneal in UHB, oxygen goes out from the surface. So to compensate this, you need to do this in oxygen atmosphere for some surfaces. But anyway, after you do this kind of treatment, you can distinguish each different surface with electron diffraction as shown here. And then after that, we grow the iron selenide films in this kind of condition. And after growing the film, you get this kind of electron diffraction pattern. And you may feel a bit tricky that it is impossible to grow only a monolayer. But if you take a close look at the intensity of this spot, you will see this kind of oscillation, which is called a Reed oscillation. And from this, it is possible to determine the time needed to grow one unit cell. So from this kind of measurement, we can really be sure that we are growing only one unit cell thick films. So after growing the film at this part of the chamber, this is the real apparatus of the experiment. We transfer it down here to do measurements with scanning tunneling microscope, which is the microscope that has the highest spatial resolution that the mankind has ever invented, okay? So we can get atomic resolution images with this microscope. And as I have been mentioning, it is also possible to do electronic structure measurements, density of state measurements using SDS. So this is a typical STM image. So this is the 50 nanometers. And by analyzing the height difference between different color domains, different colors, you can obviously see that this is the 1 unit cell part, and this is the 2 unit cell part. And if you do SDS mapping, it is also possible, you can get the electronic structure as shown here. So we do this kind of measurement, and after we are sure that what we made is very nice system, very nice film, we do more precise measurements. So we now do really fine measurements with STM, and if you, these are the results of this high resolution measurements. So you will see something like this. But the film itself, after the film deposition, it should only show this kind of periodicity. But in reality, the periodicity, what is shown here is something like this. So to analyze the periodicity, we take a Fourier transform of these images, which are like this. And these are the 1 by 1. And you will see additional spots here, which correspond to the periodicity here. And if you do real careful analysis, you will see that this is a √13 by √13 periodicity. So actually, this data is taken for a sample film grown on the √13 by √13 surface. So this really means that we can measure the surface periodicity through, even though we have grown the units, 1 unit cell iron selenide film on top of it. And then we do STS measurements. So this is for another sample, but these spectra show the density of states measured at different points of the sample. And you see this quasi-particle peak here, as well as a superconducting gap. And it shows a little difference depending on the actual sample position, as shown here. But anyway, we have grown a nice film, and then from this measurement, we know these are very nice. These are showing superconductivity. And then we do some statistical measurements. We take these STS curves at a lot of points and get distribution and try to get the mean value of the superconducting gap. So this is for the 1 unit cell system, but you can also do this for 2 unit cell system. And in this case, what we find is that the periodicity is only 1 by 1, and the STS curve shows the same feature. So in the 2 unit cell film, there's no dependence on the surface of the substrate. But as I've been saying, for the 1 unit cell, there's a lot of difference, as shown here. So the Stm image itself shows difference, and the electron structure. So this peak position depends quite drastically on which surface the film is grown on. And if you do high resolution measurements to deduce the superconducting gap, this also, the quasi-particle peak position also shows quite big difference. So this data really shows that the superconducting properties of this monolayer film depends on the surface, substrate surface. So let me just briefly describe how we can interpret this. So this peak position here actually corresponds to the doping level of this system from the substrate. So we take this position in the horizontal axis and take the superconducting gap size deduced from this graph in the vertical direction. So these 4 points are the data from our measurements. And we can also take the data from the literature, which did something a bit different, but basically the same thing. Same kind of data is obtained in this work. And these are the points. And after we make this kind of a diagram, we see that there is some kind of a superconducting dome structure, which has been observed also in cuprate high temperature superconductors. So from this kind of a analysis, we can really be sure that there is an optimum doping level for this system, and to use the proper surface is very important. So short summary of this part is what we wanted to do was to determine how the superconducting properties of this high temperature superconducting iron selenide film depends on the STO surface. And the answer is yes, it does depend quite drastically on the surface. So we have achieved this by carefully controlling the surface structure. And I only explained very briefly, but this diagram here can be understood by the amount of occupancy vacancies at the surface. Okay. So now let me go to the next topic, which is about the magnetic topological insulator. In these 20 years in condensed matter physics, the Dirac systems, the first example is graphene, have been very popular among experimentalists and also theorists in condensed matter physics. And I think there was a session about the topological insulators, but at the surface of these topological insulators, there is also a Dirac system like here, as shown here. And just to give you an idea why we call this a topological insulator is that if you calculate some index according to the band dispersion, this topological insulator is distinct from a normal insulator or the vacuum. So you cannot continuously deform this topological insulator into a normal insulator. This is the same thing as the situation where you cannot continuously deform a donut into this cup here. Okay, so at the boundary although they are same insulators, since you cannot continuously deform this into this, you need to have something different, something metallic. So that is the reason why there is always a metallic edge state or a surface state at the surface of this topological insulator. So the very, and then since this surface state dispersion needs to be spanned within all the gap as shown here, in the simplest case, this becomes a Dirac cone. And the very important point is that at wave number 0 here, as long as this time reversal symmetry is preserved, this band always needs to cross at this Dirac point as shown here. And the typical example of a topological insulator is something like a bismuth selenide or a bismuth telluride as shown here. Now, what we want to do in our study is to break this time reversal symmetry. So in this case, what happens, as I explained, this Dirac point is conserved by this time reversal symmetry. But if you break it, now you don't need this crossing and there will be a gap here. But this is another new topological state. So there will be another edge state, topologically protected edge state as shown here. So to say it more simply, in a usual topological insulator, the interior is insulating and only the surface is conducting as shown here. But in a magnetic topological insulator, the bulk is insulating, the surface is also insulating, and only this edge is metallic. And this metallic edge state is very important because it can carry current without any dissipation as shown here. So this phenomena is what you call a quantum anomalous Hall effect. So it is a quantum Hall effect without any magnetic field. So this was predicted quite a long time ago, but only realized 7 years ago. This is a rather new phenomena. So this was realized in a system like this, where the magnetic impurity was doped to break the time reversal symmetry in topological insulators. So this is a rather new study that is currently going on quite extensively. But if we extend this kind of study on magnetic topological insulators, what we can expect in theory is that we may be able to realize a magnetic monopole, or we can expect to see some novel magneto-electric effect, which is said to be related to axion physics in high energy physics. So we want to continue to study this quantum anomalous Hall effect. But as I told you, mostly the studies of this quantum anomalous Hall effect uses magnetic impurity doped topological insulators. So this is a topological insulators, and inside vanadium or chromium atoms are doped. So they induce the time reversal symmetry breaking. But at the same time, since this is randomly distributed inside the crystal, it induces inhomogeneity and it induces additional things. So that is the reason at the present moment, this quantum anomalous Hall effect realization is limited to very low temperature, 2 Kelvin at maximum. So the motivation in this study, can we induce time reversal symmetry or time reversal symmetry breaking or magnetism into this topological insulator with an alternative method? So that is the motivation of this study. So basically, to say it simply, the answer is yes. We have found a new method to induce magnetism into a topological insulator. So what we have fabricated is this kind of system. So as I told you, bismuth selenide is a usual typical topological insulator. And we can grow nice films of bismuth selenide. But what we find is that it is possible to incorporate an ordered monatomic layer of manganese atoms inside the topmost layer of this material. And now the top layer is what is written here: manganese, bismuth, selenium 4, as shown here. So how we make this? It is very simple. We just deposit bismuth and selenium on top of a substrate. That is how we made this bismuth selenide film. And then we initially tried to grow manganese selenide on top of the bismuth selenide, but eventually what we found was that manganese does not grow on the top. It rather goes inside the bismuth selenide to make this kind of a new heterostructure as shown here. And this shows the comparison of the usual topological insulator bismuth selenide and the magnetic topological insulator as shown here. So in this case, you will see this Dirac cone without any energy gap. But in this case, what you see is a gap between the upper Dirac cone and the lower Dirac cone. So by incorporation of the manganese, we can obtain this gap opened topological Dirac surface state. And to confirm if this really is coming from the magnetism, we did XMCD. And what you see here is that what you're doing here is you irradiate light, circularly polarized light, which has an angular momentum. And if the material is magnetized, has magnetization, depending on whether this is this helicity is left-handed circular polarized light or right-handed polarized light, the absorption intensity of the light is different. And by taking the difference of these two spectra, you can determine whether this is magnetic or not. And according to this study, we are sure that this system has magnetism. And this is also supported in our squid measurements. So we can also do this kind of a magnetic extension to another topological insulator, which is bismuth telluride, as shown here. And in this case, what we found is that you can incorporate 4 layers of manganese inside the original bismuth telluride, as shown here. This is a transmission electron microscope image, and each of these protrusions represent atoms, okay? And in this case also, we have succeeded in measuring a gapped Dirac cone as shown here. So to summarize the second part, the motivation was to find another method to make a magnetic topological insulator rather than doping with magnetic impurities. And the answer is that it is possible to incorporate an ordered manganese layer inside the topmost layer of the topological insulator. And of course, as I told you, the quantum anomalous Hall effect realization at high temperature, this is what we really want to do. And at the present moment, we are not successful, but together with collaborators, we are trying to do this kind of measurement. And also, this system is also very interesting in terms of two-dimensional van der Waals ferromagnets. So this is another new field which has started like 2 or 3 years ago. So we hope we can use this material to get further insight into the magnetism of these 2D materials. So with that, I would like to summarize the whole talk. So in the first part, I hope I have been able to give you an idea of what we are doing about high temperature superconductors in the atomic layer systems. And in the second part, I hope I have been able to give you an idea of what we are trying to do in the magnetic topological insulator business. So this is, finally, I'd like to acknowledge the present members in our group, as well as the past members. And also we do a lot of work outside the lab, at synchrotron facilities, also national research labs in Japan, also other universities, and also we get theoretical support from a European group as shown here. So with that, I'd like to close my talk, and thank you very much for your kind attention.
So nice talk on superconductivity and scanning, tunneling, spectroscopy, all. So now the session is open for discussion. have any questions, please. Yeah. Any question? So I have one small question. During the scanning tunneling spectroscopy measurements, is there any scope to introduce the magnetic field during the measurements?
Yeah. So actually, our system, in our system, it is capable to apply a field perpendicular to the sample as high as 8 Tesla. And actually, we have never tried this, but now one of our students is now trying to do this kind of measurement to see the vortex structure.
Here.
Yeah. So as shown here, we can apply a field. Yes.
So how this microscopy is different than the spectroscopy? Generally, what is the main difference about STM and STS?
Okay. So in STM, you are scanning, basically you are moving the tip. And in STM, you try to maintain a constant tunneling current.
Okay.
So to do that, we use a feedback loop. Okay. And in an STS measurement, we turn off the feedback loop.
Okay.
And one difference is that we turn off the feedback loop, and another difference is that we basically fix the tip position on the sample. Okay.
Oh, good. Okay. So okay then. If we don't have any questions from audience, let's thank the speaker once again. Okay. Nice talk on superconductivity.
Thank you very much.
So let's go to the second talk of this morning section. The second talk is by Professor Uday Narayan Maiti. He's going to talk on water splitting by single atom decorated electronically tuned metallic selenide. Uday?
Yeah, can you?
Yeah.
Can you see this?
Now. Yeah. You can continue now.
So let me just a moment. Just a moment. There is some issue. Okay. Yeah.
Yeah.
It's fine. Okay, I guess. Yes. Okay. Good morning, everyone. Myself, Uday Narayan Maiti. I belong to Department of Physics, IIT Guwahati. Before I start, I would like to thank the organizers for giving me this opportunity to present our work here. Today, the title of my presentation is Water Splitting by Single Atom Decorated Electronically Tuned Metallic Selenide. As you know that the rapidly depletion of fossil fuel and its negative impact on the emission from this fossil fuel combustion on climate as forces us to go towards the green technology, that is the renewable energy technology. But there is one critical issue with all those renewable energy conversion or harvested technology, that their intermittency. So you cannot have the sun in night, or you cannot blow wind on demand. So you must have a efficient energy storage technology so that you can use the stored energy on demand. And not only that, the converted energy, the harvested energy from this energy harvester, you don't want them to use the time they are converting, they are harvesting. Okay, so you want it to use when you want. But this is one thing. And also, if you consider the solar cell and wind power, they can give you high energy, but they cannot give you high power. Because whenever you want to use this converted electricity for the high power application, they are not sufficient. So you need to store it in certain storage system, and then we can use it as energy on demand. For this, I am particularly interested here, which I am going to talk about, the storing this electrical energy in terms of the chemical fuel hydrogen. As this schematic shows, the electricity produced by all these renewable energy resources can be used to break the water into hydrogen and oxygen, and this hydrogen can be used as a green fuel, because this hydrogen, when it is burned, it produces only the water vapor. So this is the zero carbon dioxide emission technology. This can be used in different areas like a fuel cell transportation, aerospace industry, all that. And they can give a very high power density. Now, to do it, to split the water into oxygen and hydrogen, one needs the two electrode, one for hydrogen evolution and another for oxygen evolution. And as you can see on the right, that this oxygen evolution process actually happens in 4 different stages of this ionic adsorption and interfacial electron transfer. And this interfacial electron transfer requires some energy barriers to be overcome. So due to these energy barriers, the requirement of the potential is higher than the thermodynamic requirement to break the water into hydrogen and oxygen. Similar steps are also there for the case of hydrogen. Now, that's why people are using the catalysts, which can lower the requirement of these potential barrier, energy barrier, so that the whole process of hydrogen evolution and oxygen evolution can happen at a much lower operating potential. To do it, there are different strategies people are using. One is that making the nanoheterostructure, where the 2 different nanomaterials, they made one-to-one, they top of one another, so that they have a synergistic effect. And the properties of one, if there is any shortcoming, that can be overcome by the another one. For example, in this case, if you consider the MOS2 and graphene, the MOS2 molybdenum sulfide, molybdenum selenides, they are known as the very good hydrogen evolution catalyst, but they have some limitation that their conductivity is low. So if there is some heterostructure formed between graphene and MOS2, so the electron, so the catalytic which happens on the MOS2, and then this graphene, this back layer, can give a high electronic, the very high electronic transportation path, so that there is a less resistive drop in the circuit. So that as a result, the voltage requirement for this hybrid heterostructures is much lower as compared to the individual one. And there is another strategy, that is downing the size of the catalyst. Because catalysis happens on the surface of the materials, catalyst materials. Now, as you can see that if the size is bigger, so the inner surfaces of those atoms cannot be accessed, only the surface atom can be accessed. So in a sense, that inner atoms of these crystals, they are dead. But if you reduce the size so that more and more the atoms can be exposed, and finally the ultimate goal, that whether it is possible to make the single atom catalyst. So it is the entirely exposed surface. But of course, the single atom catalyst, they are not stable. They must be stabilized by some substrate effect with some electronic interactions. We have actually, even though there are already different research is going on in these 2 fields, but there are still certain limitations. The limitation, particularly development of suitable heterostructures for state-of-the-art performance. Whatever people have found that even if we are doing the heterostructures, the performance is not improving drastically. The performance is slightly improved. I am going to explain also the same, that why this is so. And then the second one is that development of single atom catalyst, because as I mentioned to you, the single atom catalyst, they are not stable. They must be stabilized, and there you must have some techniques, some protocol to develop the single atom catalyst in an efficient way. And also finally, this is more critical, that is stability at large current, because whenever this oxygen evolution and hydrogen evolution happens at a large current, there is always a tendency of detachment of those single atoms from the catalyst, so that after a certain long-term operation, they becomes an inactive catalyst. To overcome those limitations, we have adopted both the strategy, as I just explained previously. One is making the efficient heterostructure, and then another is that the downgrading the size to the single atom catalyst. So first one, this heterostructure formation we have done to improve the HER catalyst, the hydrogen evolution one. And there is another counterpart, that is the oxygen evolution. For that, we have used the single atom catalyst to overcome the energy barriers, so that overall the two materials can give very high performance in the water electrocatalysis. Here is our strategy. What we have done, we have used a trimetallic oxide nanoseed structure directly grown over nickel foam. And then by making the selenization, we have made a heterostructure, that is bimetallic selenide heterostructures. So here a chemical dealloying happens. It's a trimetallic nanoseeds turns into a heterostructure, and this is a nickel, cobalt nickel selenide and molybdenum diselenide heterostructures forms over the surface. And this is the FES image of the corresponding sample. As you can see on the top two figure, these are the field emission scanning electron microscope image, where you can see the network of 6 structures of trimetallic oxides, and the surfaces are very smooth. But when we made a selenization of that, you see that the same network structures retain, but the surface looks much rougher. But when we inspected at a high magnification of these selenide structures, we have found that these bigger seeds, on the surface of these bigger seeds, there contain some molar seeds, very small seeds of a dimension of thickness of 3 nanometer vertically standing over there. We inspected those to know the crystallinity of these samples as well as the phase of these particular materials. We have done the Hrtm, high resolution transmission electron microscopic imaging, and we have found that at high magnification we have found there are some layers, and these layers, there are 4 layers of some layered material, and the layer distance, the interlayer distance, is around 0.78 nanometer. Whereas in the bulk, we started with the trimetallic selenide, trimetallic oxide to trimetallic selenide, and we expect that there is some selenide structure may happen corresponding to the molybdenum diselenide. But we found that for bulk diselenide, the interlayer spacing is around 0.68 nanometer. So there is a interlayer expansion here, in this particular structure. This interlayer expanded structure has very importance in HER performance, because whenever it has already been done by theoretical calculation that whenever this interlayer coupling is less, then their HER performance is higher. And also this edge-oriented structure is the perfect structure for hydrogen evolution reaction. Why this is so? Because for the molybdenum diselenide or molybdenum sulfides, their edges are highly active hydrogen evolution catalyst, because they can efficiently transfer the electron to the reactant to the water molecule, but whereas their basal plane is inactive. So whenever there is this edge-oriented structure, they are vertically grown over this base substrate, then it is expected to have the better catalytic efficiency, which is not possible with the face-to-face stacking or the face-to-face heterostructure. And this base one, the base plane on which this particular nanoseeds grown over here, we have checked with the atomic resolution Hrtm imaging, and we have found that the interlayer spacing of 0.197 nanometer and corresponds to 311 plane of the cobalt nickel selenide, and also this 1.173 nanometer, it corresponds to 313 plane of the cobalt nickel selenide. And there are, in the high resolution image, we can also see some vacancies, and the stacking faults are also clearly observed. And these vacancies and the stacking faults, they are known to give very high catalytic performance, because in the vacancy side there is an uncoordinated bonding. So this uncoordinated bond gives a very high catalytic performance. So what we have found here, that these, because these planes are little bit, the separation is little bit higher than the molybdenum, bulk molybdenum diselenide, to confirm that whether these nanoseeds, vertical nanoseeds, they are really the molybdenum diselenide or not, we check the XRD, and from the XRD we have found that mostly the major peaks matching with the nickel cobalt selenide, but we cannot, this is here what we expect a peak around this position from the molybdenum diselenide. It is not possible at a low resolution scanning, but when we have done the high resolution and very slow scan of the XRD, we have found that at around between around 12.5 to theta value, we have found a peak, the broad peak, which corresponds to 002 plane of MOS2. Because in this case, interlayer spacing is higher. Not only that, there are some disorder. So that's why this this peak is broad and not well defined. And we have also inspected from the Raman spectra that whether the AC2 really present or not. We have found that characteristic peaks from the molybdenum diselenide, and so all these this Raman, XRD, as well as TANE confirms that there is a formation of molybdenum diselenide, and the vertical structures which we have found from the Hrtm. These are the molybdenum diselenide, but with the expanded layer. Then we have checked the XPS analysis, X-ray photoemission spectroscopic analysis, to know the ionic state of the metal elements which are present within these materials. And what we have found that the top one, these are the cobalt, nickel, and molybdenum corresponding to our heterostructure selenide, whereas the bottom one corresponds to bimetallic selenide. As expected, in the bimetallic selenide, there is no molybdenum is here. But in the molybdenum case, you can see there is also presence of the peaks corresponds to the molybdenum diselenide. But there are also peaks corresponds to molybdenum oxide. So we expect that there are partial conversion to molybdenum diselenide, but there is some molybdenum oxides also, but those are, we expect that those remains in a amorphous phase because we cannot find them in a XRD, neither in the Hrtm image as well. But when we inspected this cobalt 2p and nickel 2p peak, what we have found that it contains we deconvoluted it, and the deconvoluted spectra has 5 peaks. So there are 2 sets of peaks. This is the red one and the blue one. This corresponds to 3+ and the 2+ states, and there is a satellite. Now, if you compare this cobalt 2p peak as compared cobalt 2p peak in this heterostructures as compared to the bimetallic selenide, what we can found that those peaks actually shifted little bit, around 0.6 electron volts. Both the set of peaks shifted by this amount, and this shifting can be associated with this heterostructure itself, where there is a partial transfer of electron from the cobalt nickel selenide to molybdenum diselenide. As a result of this partial electron transfer from the basal plane to the protruding nanoseeds of the molybdenum diselenide, there is a slight increase of the binding energy for both in the case of the cobalt and the nickel. So, and this electron enrichment in the molybdenum site has positive effect on the catalytic performance. So here is the hydrogen evolution catalytic performance, and this is the linear sweep voltammetry curve. As you can see that when the voltage is increased from 0 towards this negative side with respect to the hydrogen reversible hydrogen electrode, what we have, you can find that the current density increases very rapidly for the case of the heterostructures. And our goal is to obtain the high current at a lower operating potential, so that the overall energy cost for the hydrogen evolution becomes very low. So you can see that here we have given that this is the eta 10, this is the over potential, the extra potential needed to achieve a current density of 10 milliampere per centimeter square. And we have found that for our heterostructures, molybdenum diselenide and cobalt nickel diselenide, it requires only 89 millivolt, whereas for other cases, the pristine oxide which we started with, it requires 190 millivolt, whereas the bimetallic selenide is still the 192 millivolt, and the other oxides and only the nickel foam, they are much higher. And how the electron transfer is happening at at a higher rate. So the reaction rate can also be estimated from the Tafel slope, the slope of these curves. From here, we have found that the slope of the curves is 65 millivolt per decade for the case of the heterostructures, which is much lower as compared to the all other catalysts, which we have tested over here. This signifies that this value, that these heterostructures actually gives very high hydrogen evolution performance. And for this, any hydrogen evolution or oxygen evolution performance, the stability of the catalyst is very important. So what we have done that stability test for a long time, and we have found that it's for several hours, it gives a very stable current density at some fixed voltage. We fixed the voltage, and then we have found that current remains nearly constant. It gives a very high stability. To inspect that what is the origin of this high HER performance, we have also done the impedance, electrochemical impedance measurement. And over there, we can see that these two are the part of big semicircle, because we have given the high resolution, so you cannot see the entire semicircle. But the point at which this semicircle touches in the real axis, this gives the charge transfer resistance. So the charge transfer resistance is the lowest for the case of our heterostructure. It is only 1.04 ohm. That means it signifies that there is a high rate of charge transfer, efficient charge transfer from the catalyst surface to the adsorbed water molecule for the hydrogen, for its splitting. We have also checked that what is the nature of these two component elements, that is the molybdenum diselenide and the cobalt nickel sulfide, cobalt nickel selenide. And we found that the molybdenum diselenide is a semiconducting in nature, whereas the cobalt nickel selenide is conducting in nature, because you see that in the Fermi energy, there is a lot of density of states. So with this, we have actually summarized or concluded that what is the origin of our high HER activity. The origin of the HER activity lies in several regions. One is that this basal plane, which is the nickel cobalt diselenide, is a metallic one, so that whatever the catalysis happenings at the edges of the molybdenum diselenide, then there is a efficient electron transfer from this surface, edge surface, towards the electrode via this basal plane, because this basal plane is a conducting, so they can easily transport the electron without much of resistive loss. This is one thing. And this edge-oriented structure gives the exposure of the high catalytic sites, so that there is a high efficiency. And here and the expanded layers gives also the very high performance. And with this, we have done our one of the goal, that is to achieve the high HER performance. Then we have targeted that whether it is possible to achieve the high oxygen evolution performance. When we tested the same material for oxygen evolution, we have found that its performance is moderate. So to improve the performance, we decorated the same materials with a single atom iridium by a novel process by the UV irradiation. So UV irradiation with the UV irradiation process, and we inspected it with the atomic resolution TEM. We have found that you can still see the cobalt nickel selenide forms, but when we inspected with the STEM, we have found that there are the single atom iridiums. You can see these white spots, single atom nicely decorated over the planes of this nickel cobalt diselenide. And this is the elemental mapping. From the elemental mapping, we confirm the presence of all the phases, the expected phases, and the uniform distribution as well. The iridium in this case, this is the XP spectra of iridium 4F. And from here, we confirm that it remains in the 4 plus oxidation states in the form of iridium dioxide. And this is the oxygen evolution performance. And here you can see that whenever we have decorated the iridium, so this corresponds to iridium decorated, the iridium decorated molybdenum diselenide and cobalt nickel diselenide structures, and we can achieve 100 milliampere per centimeter square current at a much lower operating potential as compared to the other catalysts. It also evident that this is a high rate performance from the Tafel slope, where we can see that Tafel slope for the case of our intended sample, the iridium decorated sample, is only 42 millivolt per decade, which is much higher, much lower as compared to the other counterparts. And here also it shows the very excellent stability up to the 30 hours of stability test. And we have also here we have given the over potential requirement to achieve different currents, 10 milliampere per centimeter square, 100 milliampere per centimeter square, and 500 milliampere per centimeter square. 500 milliampere per centimeter square corresponds to a very high rate of hydrogen evolution. We can see that it is within the 300 millivolt we can achieve this performance.
Yeah.
For the case of we have this we have done the surface oxidation, we have done the XPS observation, and from the XPS observation we have found some interesting features that after the OER test, the molybdenum actually washed out from this sample, but still the stability of the catalyst is there. So we confirmed that there is no role of molybdenum. So the molybdenum diselenide which is there on the top of the surface, they are actually detached during the OER process, but this does not hamper the high performance of this catalysis. But also during this process, there is a partial oxidation of cobalt and nickel. You can see that this corresponds to the oxohydroxides of cobalt nickel oxyhydroxides. So partial oxidations happens over here, and this partial oxidation is also evident from the Hrtm image. The inner layers corresponds to the selenide structures, whereas the top layer, surface layer, corresponds to the oxyhydroxide structures. And we have confirmed this is the comparison of our catalyst as compared to the other existing catalyst. Here is the eta value, that is the over potential required, and the Tapel slope. You can see that in this this coordinate, our particular this heterostructure selenide and also the single atom decorated heterostructure selenides give both the high value in the OER and the HER. And we have done also, because we have done both the HER and OER, we have tested the overall electrocatalysis process with the use of the sunlight. We have actually taken these two catalysts into electrodes and use a solar cell to convert that, whether this solar cell can actually convert or split the hydrogen into hydrogen and oxygen or not. There's a efficient splitting of the water. So we confirm that it is a self-sustained system, so that we can directly convert from the solar light to hydrogen and oxygen. So here is my group, and these works which I presented is actually done by my students Abhishek. It is his own work, and I am just presenting here only. And these are my collaborators, Professor Sanguk Kim from KAIST, and Professor Subhradeep Ghosh from our same department, and Anki Reddy from the Chemical Engineering Department, and Professor N. Padma from the BARC, the Bhabha Atomic Research Center. And I would like to also thank our my funding agencies, ACRB, BRNS, and DRDO and CSIR for giving the funding, so without which it is not possible to do all these measurements. Thank you very much.
So now one short question.
Yeah.
Can I ask?
Yeah.
Yes.
Yeah. So is magnetism playing any role here? Because you have this cobalt and nickel, both are magnetic materials.
Yes. So this is actually a good question. So for the high catalytic efficiency, which orbital, whether it is T2G states or E2G states, I mean, which states it is there, that also plays a major role, but we have not done this calculation yet. The theoretical calculation is actually going on. Maybe we can present the better picture in a couple of days. Okay.
Okay. Then any question from the audience? If not, let's thank the speaker. It's a nice talk on catalysis.
Thank you. Thank you.
Yeah. So Debashish.
Yeah, I think you can close the session because, yeah. Okay. Subhash, you can close the session.
Yeah, you can formally close the session, Subhash.
Okay, I can leave, that means.
Yeah.
Okay.
So then a session is now closed. Okay.
Okay, thanks to the speaker and the chairperson. I think we have 5 minutes of gap between the next two sessions, so that the new chairperson can take over and the speakers can list their slides.
Right. So my name is Osamu Jinuchi. I will be the next chairperson, and we'll convene. So, Professor Kuze, are you there? When do we start?
I think we can start on time.
On time. Okay. So we'll be starting from 10:05 for India, and 13:35 for Japan, Tokyo time.
Yeah, that's fine. Yeah, thanks.
Okay, thank you. Professor Ito, would you try sharing the slide? And
Okay.
please. We don't see it yet. Now we can see it. Okay.
Okay.
Yeah, it works. Yes. Thank you. So the next session will be the topological field theory and the structure of nucleus. And I'm chairing this session, Osamu Jinuchi. And the first speaker is Professor Ito from TokyoTech. And he will give us the talk on the TBA equation and resurgent quantum mechanics. Maybe we can start.
Can we start?
Yes, please.
Yeah, thank you very much for introductions. I'm very happy to join again this joint meeting. My name is Katsushi Ito. I'm going to talk about the TBA equations and resurgent quantum mechanics. And this work is based in collaboration with Marcos Marinho at Geneva University, and Hongfei Xu, my former student. He's in Nordita, Stockholm now. So the contents of my talk is the following. First, I gave some introductions, and then I explained the Wkv analysis applying to the quantum mechanics, and it reformulate in the language of integral systems. Then I gave some example with cubic potential problem, and I will end this conclusion and outlook. That's the contents. So introductions. I'm going to treat the one-dimensional Schrödinger equations. And as you know, these equations can be exactly solved only a few cases, like a harmonic oscillator and so on. So then we need approximation methods to solve understanding the structure of these equations. And Wkv approximation is one of the methods to solve the Schrödinger equation. Then I explain Wkv expansions. So Wkv expansions, we take the wave functions, Schrödinger wave functions expanded in the Planck constant h bar. And if we systematically expanding the solutions in terms of Planck constant, we have this kind of formula, and the P here is the expanded by the Planck constant, and Pn is the function of Q, and it can be solved recursively, but the leading term is the represent the classical momentum of the system. That's the structure of the Wkv expansion. So as we learn in the quantum mechanics in the undergraduate course, the Wkv method gives the leading approximation to a problem in quantum mechanics. So for example, we know the energy spectrum by the Bohr-Sommerfeld quantization conditions. And one can also compute the tunneling coefficient in the scattering problem. So, so this Wkv series is asymptotic series in h bar. So actually the convergent radius is exactly at 0. So to think about this expansion seriously, we need to handle the power series with convergent radius, the asymptotic series. And sometimes when we apply the Wkv approximation in a more complicated potential problem, we need to take the contour of the integration in the Wkv series. We extended it to the complex plane. So there's arises some ambiguity in the choice of contour. So it arises the problem in ambiguity in the connection problem. And also sometimes we have non-perturbative effects in h bar. So it's not expanded in a series expansion in h bar. So so naive Wkv series expansion doesn't care about this kind of problem. So we are going to work out this kind of problem in the following way. So so exact treatment of the Wkv expansions was treated by Boros in 1988. So the asymptotic expansions, we need to take some appropriate resummation method. So it is called the Borel resummations method of asymptotic expansions. And to treat the some connection problem, we need to think the Schrödinger equation originally defined on the real axis, but it's very convenient to extend it, think it, this equation in a complex domain. And also h bar, it is some fixed constant in physics, but we need to freely treat this Planck constant as some fixed parameter. It might can take the complex value parameters. So Boros think this Schrödinger equation in extended manner, and he formulated ambiguity problem as the Stokes phenomena of the differential equation. And also the non-perturbative effect is treated by the way of resummation method. It is called Resurgent method, developed by Eckhart. So he applied this Schrödinger equations, these approaches to solve the spectral problem of the Schrödinger equations. Then we treat the properties of the WKB period, which arises in the Bohr-Sommerfeld quantization conditions. And he found some discontinuity in the Planck parameter. He showed that this the classical leading approximation of the WKB periods and the discontinuity structure determine the exact WKB periods exactly. So this method is called the analytic bootstrap, or in mathematical language, it's a kind of Riemann-Hilbert problem. So he solved this Riemann-Hilbert problem exactly, and using this extended Schrödinger equations. And also he applied the WKB method of the periods and the exact quantization conditions, which is a slightly generalized version of the Bohr-Sommerfeld quantization conditions. And he can able to determine the exact spectrum of quantum mechanics. But his formulation is rather complicated. So if he explicitly worked out only for cubic and quartic potential cases. So there appears another way of understanding the structure of the Schrödinger equations was observed by the in the context of the integral models was found by Dorean, Tateo, and Bazhanov, Lukyanov, and Morochkov in 1998. So this is called the Odim correspondence. So I explain a little bit about this correspondence. And it is a relation between spectral analysis approach of ordinary differential equations and the functional relation approach to the quantum integral models. So we start from the differential equations with of this form. And this is the situation, Schrödinger equation with monomial potential cases. And Dore and Tateo found this this solution of this second order differential equations is closely related to the structure of the integral models appearing in the 6-vertex models. So I use 2 slides to explain how to relate two very different objects. So first, I try to find asymptotically decaying solutions in some complex regions. So its complex plane is divided by several sectors. And when, for example, Y0 is the decaying, asymptotically decaying solutions, which is uniquely defined in this particular Stokes regions. So they write out some set of asymptotically decaying solutions in the different sectors. So, and then we can construct the set of solutions to the second order differential equations. And one can construct the object from the Wronskians of these solutions. So this is independent of the, this object is independent of the coordinates. and only depend on the parameter of the differential equation. In this case, we have energy. So, and one can see the asymptotic behavior of the these y functions, and it is given by the some sort of Born-Zormanfeld period. And also Wronskians is represented by 2x2 determinants, and using a relation satisfied by the 2x2 determinants. So this y function is shown to obey this kind of function relation. So this is called y system. And one can use these y systems to derive the logarithms of the y functions obey the integral equations. So this is called the thermodynamic Bertrand equation in the context of integral models. So this is called TBA equation appearing in the title of my talk. So investigating these equations, integral equations, one can estimate the free energy of the systems, and the large limit, the free energy proportional inverse proportionally to the way the coefficient is characterizing the central charge of the corresponding integral system. So in the present case, it gives the two-dimensional conformal field series belong to this special class of these minimal models. So that's in this way, the Schrödinger equation is related to certain integral models. That I'm going to explain more bit using the Schrödinger equation. So my main result in this talk is to presenting the TBS equations covering the exact Wkv pairs for general polynomial potentials. So and also we present TBA equations also provide a generalization of the ODIM correspondence found by Dre, Tateo, and Vaginal Kuki for monomial potential cases. So then from now on, I want to discuss some relation between these quantum mechanics and the TBA equation for generic potential. Then I discuss some example. The simplest example is the cubic potential. So I want to explain some numerical results related to the the solution of the TBA equations. So I will talk about the Wkv methods and its application to the TBA equations. So let me start again from the Schrödinger equations. We have a little bit simplified version that the mass parameter is half. So we have no additional parameter here. So, and we can expand this Wkv solutions with this exponential term is expanded by h bar. And Q is shown to obey the nonlinear Riccati equations. And with the PQ is denoting the classical moment. And Q is inserting this expansion in these equations and divided into the even and odd part. And we can see that the odd part is represented by the log derivative, derivative logarithm of even part. Then, so the solution is totally represented by the even power of the Planck constant. And so this nonlinear structure of the equations shows that the higher power series in H bar is can be determined recursively. So then now we are going to consider the situations that the polynomial potential is given by the polynomial in Q. Then so we are thinking about the this equation in a totally complex plane, and one can suppose this this Q and other variables is complex. Then the Bohr-Sommerfeld periods or WKB periods can be extended in a complex region. Then we can consider this kind of Riemann surface, which is given by the polynomial of order here R+1. So this gives a higher genus Riemann surface, and one can define the WKB periods on this Riemann surface. Since PQ is expanded by H bar, so this WKB period has the expanded by H bar accordingly. So the problem is that this is the asymptotic series in H bar. So so following up the Boros, I will use the Borel dimension. So that is first I use this this is suppose this is the divergent series where the coefficient is the order of factorial, and the Borel transformations mean that so we define the power series by dividing the factorial of factor n. So and this decreases the divergent properties of the original series, and sometimes it's convergent series. And then we can perform the Laplace transformations to this. And if this have a convergent finite radius, so this gives the also well defined. And if one take asymptotic expansion of this series, we can recover the original series. Then, but this function is more good functions than the original functions, because it can be extended in other analytical continued functions. So it can be applied in other regions in complex plane. So this is called the Borel dimensions. And the typical famous examples is from the Euler. So these alternating sum of the power series with factorial is Borel transformation gives the geometric series. And if one can take the Laplace transformation, it gives some kind of incomplete gamma function. So this gives the another expression of, which is valid in other region in complex plane. So one can use this function to explore this represented the values represented by this power series. But sometimes the Borel transformed functions have a singularity in the complex C plane. So so that's cause a problem to define the Laplace transformations. So for example, one can, so this arises, this singularity causes some, one can not define Laplace transformation appropriately. Then to define the Laplace transformations, we slightly move the contour to avoid this singularity. two ways of avoiding singularity, the upper and lower. So the difference arises cause a discontinuity to the Laplace transform function. So that's so this is numerical estimations of the Schrödinger equation for cubic potential. So this continuity is helpful to understand the whole structure of the problem. So let us consider the cubic potential represented by this. And we have two cycles. The one is classically allowed regions. The other is classically forbidden region, which is depend on the energy of the potential. So it is shown that this we can see that for this classically allowed interval, when investigating the asymptotic series, it is shows the discontinuously along the real positive axis. And also classically forbidden cycles show the continuous along the positive real axis. And discontinuity formula, but two objects are shown to be related. This is shown by Delabarre and Pham in 1999. And so this is a discontinuity formula. And actually this discontinuity of the classically allowed period is related to the another period, Wkv period. That's a good formula to write down the functional equation for this Wkv period. And one can also formulate the Boson-Moffett quantization conditions for the Wkv period. So this is a typical Boson-Moffett quantization condition, and one can get the perturbative spectrum from this one. But it turns out this only shows the perturbative structure of the spectrum. And to get the non-perturbative structure, exact spectrum, including non-perturbative ones, one needs to modify the Boson-Moffett quantization condition. So this is also discussed in a variety of papers. On the cubic potential cases, it turns out we need to include the non-perturbative term. And this solving the this quantization condition gives the exact energy spectrum. So I have a little bit short time. Then I applied to this the Delabarre-Pham formula for generic type of polynomial potentials. And so this is characterized by the classical period associated with the allowed regions, and also formulate the introduce the periods for not forbidden regions. So both periods are necessary to formulate. So and then this continuity formula shows that one can have the TVA equations for this classical Wkv equations. And this this MA denotes the classical Wkv period. And so LA is, well, I lost some formula here, but this is 1 plus exponential is the LA. So then this integral equation actually determines the function EA, and one can calculate the free energy, and also this EA to find the exact spectrum for this polynomial potential cases. So let us apply this method to the cubic potential. So first, I write down the TB equation for this one. So in this case, we have only two periods that obey this kind of equations. And one can apply this the estimated free energy to obtain the corresponding integral models, which is in the ultraviolet, this corresponding to the conformal field theory, represented by this coset model. And other interesting applications for this potential is these imaginary potentials. This is called the PT symmetric Hamiltonian. So this is not Hermitian potential. So it's not standard potential problem, but it has some PT symmetry, is a parity plus complex conjugation symmetry that guarantees the spectrum of this problem is real and positive, discrete in some region of parameters. So one can also formulate the TB equations for these cases, but I will not explain it later, not details. And one can also apply the Bohr-Sommerfeld or exact quantization condition for these systems. So then first I show the numerical result. This is the computation of the Boros spectrum, which is the associated value of Planck constant for given energies. So one can find the Boros spectrum by solving the TB equations. And then I apply this Planck constant to the computed spectrum obtained by other quantum mechanics method. And so gives the relation gives the we start from this parameter and give back to the obtained parameter is very close to 1. And so actually this works for this TB equation works for this cubic potential. And one can also this very symmetric point, which recover the original Dore-Tateo's ODIM correspondence. And also one can check the numerically obtained spectrum. So the second column is the spectrum that obtained from our TB equation with exact quantization conditions. And the first column is the obtained by some standard method for cubic potentials. And the fourth, third and fourth column is the TBA plus Bohr-Sommerfeld and Bohr-Sommerfeld approximation. So our method is very close to these exact approaches, approximation approaches, compared to the other way of quantization method. So the conclusion is that we have provided an efficient approach to solve the spectral problem for arbitrary polynomial potentials in one-dimensional quantum mechanics. The solution takes the form of TBA system for the summed quantum pairs, which generalize the ODM correspondence proposed by the Dore and Tateo. So this is a further perspective. So I have an application to other problems to this correspondence, but I have no time to explain here. Okay, thank you very much.
Thank you. Okay, thank you very much, Professor Ito, for your interesting talk. Since we are running out of time, so this is we are now open for the discussion. But is there any quick one or two quick questions to Professor Ito?
May I ask one question?
Yeah.
Yeah. So you said it is applicable to one-dimensional Schrodinger equation. So can't we generalize it to higher dimensions, or?
Well, just one of the problem is the very symmetric cases. The three-dimensional with centrifugal term, like Kepler problem or the Stark effect and so on. But in generic three-dimensional problem is still difficult to apply it.
Okay, I see.
Okay, is there any other quick questions? Okay, thank you very much, Professor.
Okay, thank you very much.
So next speaker is Professor Takashi Nakamura. He's going to tell us about the extreme nuclear physics. So the title is exploring the extreme of nuclear landscape using radioactive beams. Yes, we can.
Yeah. Can you see the slide now?
Yes, we can see it.
Okay. Thank you very much. Thank you very much for giving me this opportunity for this nice workshop. Let's see. Yeah. So today I'm going to talk about exploring the extreme of nuclear landscape using radioactive beams. I'm Takashi Nakamura from Tokyo Institute of Technology. So since this is the only talk from nuclear physics, I think I'd like to spend some time on introduction. I'd like to emphasize the importance of clustering phenomena, which is related to the hierarchy of quantum particles. And then I'd like to explain about the nuclear landscape at the limit, especially about two neutron halos. And then I'd like to focus more on the Dyneutron clusters in neutron-rich nuclei, and then show you the recent experimental results on dyneutrons on boron-19, helium-6, and lithium-11. And finally, I'll give you summary and perspectives. So as you are probably aware, the existence of human beings depends subtle balance of nature. For instance, a notable example is this triple alpha reaction, which is nothing but a detour for the synthesis of element carbon-12. So probably you know that carbon was not produced in the Big Bang. This is due to the instability or no stable nuclei in mass number 5 and 8. So the triple alpha reaction can be explained like this. So first, two alpha particles, namely helium-4 nuclei, meet to produce barium-8, which is semi-stable state of about 10 to the minus 16 seconds. If barium-8 during this time meet alpha particle, another alpha particle, then it can have a possibility to form carbon-12. But because of this large energy gap, actually it doesn't go smoothly. So the Fred Hoyle insisted that if there is no state around barium-8 plus alpha energy, then the human beings don't exist. We don't exist. So, so he actually insists that there should be some state here. And indeed, just after this prediction, this state was observed in nuclear physics. This state is now called Hoyle state indeed. And this state is also interesting because of, in terms of nuclear structure, called alpha cluster state. You know that atomic nuclei are made of neutrons and protons, and you can consider neutrons and protons are building blocks of nuclei. But in fact, for Hoyle state, alpha particles are the building blocks. So this is made of 3 alpha particles. And this alpha cluster develops near the threshold like this way. And this rule is called Ikeda diagram. Okay, now I'd like to ask you the question, clustering can be a key to quantum hierarchy, to understanding quantum hierarchies. You can see quarks, hadrons, nuclei, atoms, and molecules. This is the standard quantum hierarchies. If you just look at the systems with strong interactions like this way, and then you notice that the proton in hadron actually is made by three quarks by neutralizing color charges like this way by three quarks, right? And nucleon can behave like a cluster. Actually, this is like a kind of composite system, but it's very stable. And this can be a building blocks for the upper hierarchy, that is nuclei, like this. So, and then you notice that the nuclear force between neutrons and protons are much weaker than the force between quarks mediated by gluons. So this is the separation of the hierarchy in itself. So now you can just look at the electric magnetic systems. This is happening actually also similarly. Like look at the atoms. Atoms are made of nucleus and electrons, which are made by neutralizing electric charges, right? And then these atoms can be a building blocks of upper hierarchy molecule. So like this way. Okay, so now I'd like to discuss so-called semi-hierarchy. And so let's take an example again, the carbon-12 nucleus, which belongs to a nuclear hierarchy. But if you excite this carbon-12 fully, then you can see 6 neutrons, 6 protons. So these belong to hadron hierarchy. But if you tune the excitation energy very close to the 3 alpha decay threshold, then you can see this whole state, right? So alpha cluster appears. Similar phenomena can be seen in hadron quark sectors. Let's take a look at the lambda hyperon. And then if you excite this lambda hyperon fully, it goes to quark hierarchy. But if you tune the excitation energy very close to the nucleon plus k-bar meson, then you can see hadron molecule like lambda 1 or 4 or 5. Okay, if you now turn to the atom molecule sectors, and then similar phenomena actually occurs in between the in the unitary limit, so-called, then you can see the Feshbach molecule like this. And we may call this intermediate hierarchy semi-hierarchy. Okay, the formation of this kind of semi-hierarchy, the threshold plays an important role, as we have already seen. And also the neutralization degree of freedom, for instance, to make alpha particles more inert, the neutralization of spin and ice spins play an important role. Okay, now we'd like to look at the neutron-rich limit. So now let's take an example, boron 11 nucleus, 5 protons and 6 neutrons. And instead of putting the energies, we just changing the protons, exchanging protons to neutrons. So if you exchange 5 protons into 5 neutrons, then you see 11 neutrons belonging to hadrons. But if you just replace 2 protons into 2 neutrons, then you can have lithium-11, which is very close to lithium-9 plus 2 neutron threshold. And you can see this kind of very exotic state called neutron halos. And you can see this Dinutrient cluster, which is the subject of this talk. Okay, now I'd like to explain about the current frontiers of atomic nuclei. So this is a so-called nuclear chart, neutron number, proton numbers, and thick blue color points are just stable nuclei, and the other thin colors represent exotic nuclei or radioactive nuclei, short-lived nuclei observed in laboratory. And then the green part corresponds to the exotic nuclei, which have never been observed but predicted. And this prediction has also very much uncertain, has very large uncertainty. And the limit is called neutron drip line for a neutron rich side, proton drip line for proton rich side. And of course, we have also questions about how heavy we can go. So the question in nuclear physics, big question is where is the boundary of existence of nuclei, the location of neutron drip line, proton drip line, and how the nuclear properties change, and how we can see the new phenomena due to weakly binding, change of surface, very asymmetric neutron to proton number ratios. And then actually we have beginning to see neutron halos, skin phenomena, dineutron neutron droplet, or neutron matter. And also, as you see here, the dark green arrows show the process called R process, which is the very important process to produce heavy elements over ions, actually. And you can see that this path is well outside of the observed region of nuclei. So we still need to explore these regions to understand how we are synthesized. Okay, and these nuclei are also relevant to the physics of neutron stars also. Okay, to explore these exotic nuclei, in Japan, we have this R-beam factory at Riken, just just north of Tokyo. And this is the only third generation R-beam facility, means that this is the most advanced R-beam facility in the world currently running. So you can see that this facility is made of many cyclotrons, actually, cyclotrons here, 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 and there. So the cascade of cyclotrons can accelerate heavy ion beams up to uranium at 345 MeV per nucleon with very high intensity. And with these high intensity heavy ions are used to produce exotic nuclei by fragmentation reaction or in-flight fission. And then with this big grips, in-flight RI separator, one can purify or transport those RI beams to one of the very unique spectrometers. Just to note that actually the element 113, the very heavy element, super heavy element was produced here and named nihonium very recently. And for the exotic nuclei, actually already in this facility, about 200 new isotopes have been observed in the frontier of nuclear chart like this, here and here. And the other important question I already addressed is where the neutron drip line is located. And so for the neutron drip line, actually it's very difficult because of the very far from the stability line, and it was established only up to Z = 8 oxygen here at oxygen 24 for a long time. But recently we have studied, actually we have searched the fluorine 32, 33 over beyond the neutron drip line, and so this is a spectrum Z over Z. So you can see 1 point corresponds to 1 experimental point, and we didn't see any points for fluorine 32, fluorine 33. It's really irrespective of the prediction that about 10 counts for this region. And then we actually conclude that the fluorine 31 is the last fluorine isotope, and also neon 34 is the last neon isotope. But the world is not so easy. We are now exploring this region. We have actually observed new isotope sodium 39 here. So the neutron drip line for Z = 11 or 12 is still being explored. Okay, now I'd like to focus more on Dyneutron clusters in neutron-rich nuclei. Okay, so here again, this is the neutron nuclear chart, but up to Z = 12 magnesium. And this black thick line corresponds to the neutron drip line. And we are interested in this neutron drip line nuclei, and especially some nuclei here, lithium-11 or barium-11, show a very peculiar structure composed of the very dense core surrounded by extended neutrons, which are called neutron halos. So I just would like to explain about two neutron halo nuclei. So this is the kind of representative two neutron halo nucleus. It's the heaviest lithium isotope, lithium-11, which should have this kind of structure, lithium-9 compact core surrounded by extended neutrons, made of two neutrons, and with very small separation energies. And the point is that any of the two body constituents, namely lithium-9 plus neutron or neutron plus neutron, are unbound, but with three body it is bound. This feature is called boromian. You can see here the boromian ring. This is actually from the icon of the family in northern Italy, Borromeo family. And this icon, if you just cut one ring, then you can see these two rings are naturally separated. Any of the ring, if you cut one ring, then the other two are separated, in fact. So this is like two rings are separated, but with three rings, it is bound like this in this case. The other feature of 2-neutron halo nucleus is it has very small separation energy. This is 2-neutron separation energy. S2n is less than 1 MeV typically, much less than the standard 2-neutron separation energy of 8 MeV or more. And these 2 neutrons have very small Fermi momentum, usually 10 to 20% of the normal Fermi momentum. So it means that it has a long wavelength. And the orbital angular momentum should be 0 or 1. Namely that these 2 neutrons shouldn't have a very large centrifugal barrier, which actually avoids the extension of these 2 neutrons, because these 2 neutrons are actually going extended by the tunneling effect. Okay, consequently, these 2 neutrons have a large radius, and which is amounts to about twice the core radius. Okay, I'd like to also I'd like to remind you about the pairing correlation nuclei. So, you know that 2 nucleons are, most of the 2 nucleons are not bound. Only neutron-proton pair with spin 1 is bound, called deuteron. But for 2 neutrons, it is unbound. But these 2 neutrons have some scattering lengths, namely interacting with each other, with a scattering length minus 18.9 femtometer. Note that this absolute value is very large compared to the nuclear force of femtometer scale. So this is rather long range property. This is rather long range property. Okay, if you put this paired neutron inside a nucleus, actually it shows so-called BCS-like pairing correlation, which has a characteristic of long range weak coupling. But many years ago, more than 40 some years ago, Russian physicist Migdal predicted another type of neutron-neutron correlation, pairing correlation on the surface of a nucleus, which is called Dinutrient Correlation, having a short range property and strong coupling. This is like BCS versus Beck in maybe condensed matter physics. So BCS-like pairing correlation has been actually known for nuclei for 60 years. On the other hand, this Dinutrient correlation has not yet established, I would say. Maybe a few examples suggested in halo nuclei, which actually is the subject of this talk. Okay, now I'd like to move on to the recent experimental results on the Dinutrient correlation. The first one is the Coulomb Breakup boron 19 with this collaboration. And the Caitlin Cook analyzed the most of the part of this data. So this was published this year in PRL. Okay, so Coulomb breakup is nothing but the process of photon absorption process of a fast projectile. So this is a relativistic boron 19 beam on high Z target, like lead target. Then when boron 19 passes by the target, it experiences a pulse of strong Coulomb force, which can be translated into an absorption of a virtual photon, like this way. And boron 19 is excited, and it breaks up into 3 particles, boron 17 and 2 neutrons. In the experiment, we measure the momentum vectors of these 3 particles like this. And then one can reconstruct the invariant mass of the intermediate excited state of boron 19, which can be also translated into so-called relative energy and excitation energy of the state. And by doing that, one can extract the Coulomb breakup cross-section, differential cross-section, and then this can be related to the product of E1 virtual photon number and the E1 transition probability. E1 means electric dipole transition probability times electric dipole photon numbers. So photon numbers can be calculated rather easily as a function of excitation energies, so that one can extract the transition probability. Electric dipole response can be directly extracted. And the characteristic feature for halo nuclei are actually the very large concentration of electric dipole transition less than 1 MeV. This is called soft E1 excitation. So about soft E1 excitation, actually we did the experiment for this typical representative halo nuclear lithium-11 many years ago, more than 10 years ago. And this is a typical, so this is the kind of B1 distribution. you can see that excitation energy here is like 800 keV. So you just added 2 neutron separation energy, you can get excitation energies. So this is like 800 keV excitation energy. So this is soft wave excitation, not as I mentioned. And the good thing about this is that one can use this kind of soft wave excitation spectrum to extract the geometry of the ground state of the halo state. So by using these equations, one can extract, for instance, the distance from the core center to the center of mass of 2 neutrons, 2 halo neutrons, Rc2n, or even the R1 dot R2. This is related to the opening angle. So in fact, with this experiment, we could evaluate the opening angle between these 2 neutrons to be about 50 degrees, which is actually a very smaller, much smaller, significantly smaller than the 90 degrees, which is uncorrelated. So this means that this is a correlated neutron, and this actually the hint of the spatial correlation and suggestion of the Dinutrient correlation itself, in fact. So back to the boron 19 experiment. So we produced boron 19 at 220 MeV per nucleon at the RIBM factory, and impinging on lead target located here. Coulomb breakup occurs. Boron 17, 2 neutrons are emitted. Boron 17 is bent by a submarine magnet with 3 Tesla superconducting magnet. Neutrons are going through a gap of a magnet and to reach a neutron detectors called nebula. So by doing that, one can reconstruct the invert mass of boron 19. So this is the Coulomb breakup cross-section as a function of relative energies. So we have actually seen very strong Coulomb breakup cross-section, and this is the translated E1 strength distribution. And from that, we conclude that this is a signature of halo. So boron 19 was not so well established before, and we now establish the halo structure of this nucleus. Also, we could extract the distance between this boron 917 core to the center mass of these 2 neutrons, and which is significantly larger than boron 17 radius, and also other important features related to halo nucleus. So we also compared our results with 3-body model by Hagino-san, which could reproduce our data almost perfectly with these parameters. And this 3-body model predict actually the Dinutrient correlation here. So theta 1,2 is the opening angle between these 2 neutrons, and at about 4 femmeter. So this is nothing but the Dinutrient correlation. Okay, I just skipped the detail of the discussion here. Okay, the second topic is about the Dinutrient cluster candidate in the helium-6 excited state. This is the Saito-san's PhD thesis subject. So she's doing much more, but I'd like to focus on the state here. So helium-6 is also a neutron halo nucleus, helium-4 plus 2 neutrons. And we are interested in this excited state here, 2+ state. And to excite this state, we use now carbon target, and 2+ state is excited, and we are measuring this helium-4 plus 2 neutrons in the exit channel. She actually already analyzed most of the things, and I would have liked to show you, but I decided not to open, and I don't open here. But anyway, what we are now doing is the correlation, making a correlation between ENN alpha and ENN, namely here. Maybe this is easier. So we can, because we are measuring all the momentum vectors, we can reconstruct the neutron energy and alpha NN energies like this. And if ENN is small, that means relative momentum between this momentum is small, and that corresponds to large spatial distribution inside a nucleus. But in fact, this is called FSI, finite state interaction. This means that neutrons are correlated outside of helium-6 in this case. But if dineutron exists, then we should see this kind of correlation, namely that we should see large ENN, large relative momentum that corresponds to small XNN because of the uncertainty principle. And indeed, this theory predicts FSI peak as well as dineutron peak. So if we can see this kind of 2 peaks, this is the kind of evidence for Dinutrient correlation in this first excited state of helium-6. And actually, we have now seen such a structure. Okay, the third topic is about locating dineutron distribution in lithium-11. This experiment was led by Kubota-san and Uesaka-san's group, but TokyoTech group has been also involved in this experiment rather deeply. And this publication was just done yesterday. This was published in PRL just yesterday. So I just would like to explain a little bit about this experiment. So this is really like anatomy of the dineutron states or two neutron halos. So we used proton beam, not proton beam, proton target on lithium-11. So lithium-11 beam on proton. But to explain simply, I just would like to use lithium-11 at the rest frame. And in that case, proton is coming and the proton hits one neutron here. And then one neutron is knocked out. And then proton is also going this way. We measure this proton as well as neutron in coincidence to know the momentum content K1 before knocked out. And also the remaining residue is lithium-9 plus neutron, which is unbound. So it decays into lithium-9 plus neutron. And this momentum, two momentum have information about K2. So we can see K1 and K2 using this method. So in this method, one can, for instance, extract the opening angles between these two momentum vectors, K1 and K2. And this is actually related to the R1 and R2 in coordinate space like this way, because you know that. So just to go into the result. So this is the K1. So K1 shows missing momentum, it's called, but if the momentum is small, that means the distribution of neutron is rather extended. So vice versa, like this. So in fact, and then this axis shows the correlation angle. So this correlation angle is plotted here. And if you can see now that actually this correlation is enhanced only in the surface region of lithium-11. This is very interesting because now one can see that dineutron is actually enhanced only in the localized region of the lithium-11 state. Namely that the dineutron is localized on the surface of lithium-9 core, not too close, not too far, like this. And the density is like -3 to minus 10 to the -3 to 10 to the minus second compared to the normal nuclear density. So like this way. Okay, so time is almost up. So this is summary. I don't need to repeat what I said. For the future, we would like to see more dineutrons. So we are planning to do the direct measurement of dineutron state in oxygen 26 in the near future. And also, we are now building a new setup for the search for 6 neutron state, hexaneutron state in helium-10. And more exotic neutron states, by studying more exotic neutron states, one can study nuclear interactions, many body effects at the limit of nuclear stability, and hopefully we can also understand neutron stars. Okay, I also would like to thank all the collaborators in this work, like this, and thank you very much for your kind attention.
Thank you very much, Professor Nakamura, for a very interesting talk. Now the session is open for the discussion. Is there any questions, comments?
Yeah. May I ask one question? So I just wanted to know, like this neutron cluster that you were talking about. So we know that our heavy nuclei have more neutrons. So can neutron cluster form there, or the nucleus can decay via this via emitting neutron clusters, just like we see alpha decay for heavy nucleus?
I see. Okay, so first of all, for heavier nuclei, it's not so easy to go to the limit because in heavier nuclei, the neutron drip line is very far. So let's see. So here you can see, so this is the currently observed nuclei, and here the neutron dip line. So we expect such very exotic neutron clusters at the limit because it's a kind of threshold effect and very low dense neutron states. So of course, heavier nuclei have more neutrons, but rather well bound. So this will show something like BCS like neutron-neutron correlation, but not like dineutron correlation.
Okay, thank
Does
you.
that, okay.
Yeah, that's clear. Yeah. And one more question, like since you have talked about neutron cluster happening in very light nuclei also, can it affect stellar nucleosynthesis in some way, or?
Yeah, that is a very interesting question. Actually, could be, but not so well understood, this one. Rather, well, so you are talking about nucleosynthesis, but this may be relevant rather to the neutron star surface region where the neutron density is rather small, so that we may see more enhanced neutron-neutron correlations there. But
Okay.
for instance, some people studied helium-4 plus dineutron to produce helium-6 in the Big Bang or something, but it didn't work, I heard.
I see. Okay. Thank you.
Is there any other questions? Okay, if not, I had actually a question. So you showed us the dineutron, the correlations studies, and I was wondering. So when you show the dineutron skins, you have the core, lithium core inside, which is described by the one body. Is there any possibility that there is some kinematics inside this lithium core?
So beyond the three-body effect, you mean?
Right. Yeah. Exactly. Yes.
I see. Okay. Yeah, that's actually interesting question. Of course, it could have some effect of core. I mean, if the neutrons are inside the core and so on and so forth. But actually, in our experiment, we are looking at lithium-9 plus neutron already. So the lithium-9 survived. So by doing that, we probably don't see much the effect of this, core neutron interactions. The very complicated effect on the core, I would say.
Yes,
But
well,
this is an interesting question, too.
Yeah, I think the most of the events are coming into the three body or three final states.
Yes,
but I was wondering if there is any missing events which actually decay into 4 or 5 body.
Yeah, that's an actually very interesting question. So so far we are using this kind of invariant mass spectroscopy, but we are now building so-called missing mass spectroscopy methods where we don't care much about the core final state. Then we can probably see something else, or yeah.
Okay, thank you very much.
Thank you.
So if there is any other quick questions, we can close the session. Thank you very much for two speakers. Thanks for the audience as well. So Professor Kuze, we recombine.
In 5 minutes. Yeah, 11:15 Indian time, 14:45 Japanese time.
The next
Hello.
Chairperson is here, right? Yeah, Debu is here. Okay.
Debu, yes.
Yeah, okay. Fine. So you start in 4 minutes. Yeah.
Yes.
Yeah.
Okay, so maybe if Professor Teriku Swama is there. Maybe we can just, hello, Professor Swama.
Yes. Hello.
Yeah. Yeah. Hi.
Hey.
How are you?
Yeah, good.
Yeah, I'm fine.
Okay. Can I just check?
So maybe you can check whether this is good. Yes, yes.
So you can see my screen.
Yes, yes, yes.
Okay, good.
Also, other speakers can test the sharing if they want during this time.
Yeah, I mean, it is. Kohei Fujikura is there?
Yes. Can I test my?
Yeah, maybe you can just show. Yeah.
I see. Thanks.
Reajul. Yes, so it is okay. So can you just change the slide and see? Yeah, it's working.
Thanks.
So Reajul is there? Reajul? Hello, Reajul?
Yes.
Yeah, maybe we can just show your slide. And
Yes.
so we have 1 minute to go. Maybe we can just start.
Okay, is it visible?
Yes.
Yes.
Just change. Yeah. Okay. Yeah. Okay. Okay, maybe I think we should start. Devasis?
Yeah. In 1 minute. Yeah.
Yeah, in 1 minute.
Riazul can unshare the screen.
Yeah, please.
I'm taking some difficulty. Okay.
Yeah. Okay. Fine.
Okay.
Yeah, Debu, you may start.
Okay, so I'm Dev Prasad Maiti from IIT Guwahati, chairing the last session of this workshop, and it was so far quite well. So in this session, we have essentially 4 talks, and after that we'll be ending. And the first talk will be by Professor Teriku Swama, and he will be talking about gravitational waves as a probe of primordial density perturbation. So Professor Teriku Swama, so your time is for 25 plus 5 minutes. Okay, you can start now. Hello.
I think you have to unmute your mic. I think.
Okay, yeah. Professor Swama, can you hear us?
You have to unmute your mic, Professor Swama. Yeah.
Hello.
Yes. Let me.
Yeah. So. Yes. So please start.
Okay. Thank you. First of all, I'd like to thank the organizers for giving me the opportunity to give a talk here. And so my talk is about the gravitational waves to probe the primordial density perturbations. And I'm Teru Akiyama, and my research field is cosmology. And the new results presented in my talk from the references shown here. And okay, let me start. So these works were initiated when I gave a series of lectures at the summer school on gravitational wave astronomy, which was held during the summer last year at International Center for Theoretical Sciences at Bangalore in India. And people, so I am here, and people circled marked by red circles are my collaborators. And in this summer school, I gave lectures on primordial black holes and its connection to gravitational wave astronomy. And the primordial black holes are getting growing interest in recent years. And this is, please look at this figure. So this shows the number of papers whose title contains either primordial black holes or primordial black hole as a function of the year. And you can clearly see that the number of paper is rapidly increasing after the year of 2016, when the LIGO announced the first detection of the gravitational waves. So primordial black hole is currently a hot topic in cosmology. Before I go to the main part of my talk, since I guess most people in the audience are not familiar with cosmology, let me use this slide just to give the basic basic facts of cosmology relevant to my talk. So this figure shows the time evolution of the universe from left to right. So this is a beginning of the universe. We don't know how the universe universe was born. At some point, the universe starts to expand, starts the accelerated expansion. So the space expands exponentially, and we call this era inflation. And during this inflation, it is thought that the primordial density perturbation, which is the spatial inhomogeneity of the energy density of the universe, this primordial density perturbation was generated from the quantum fluctuation of the scalar field. And this inflation is caused by the vacuum energy. And after inflation ends, this vacuum energy decays into the particles, relativistic particles, and the universe becomes universe then is filled with hot radiation, and the universe continues to expand, and the temperature of the radiation gradually decreases. And when the temperature becomes as low as 3000 Kelvin, then the plasma becomes neutral, and this density perturbations started to grow by the gravitational instability, and they finally become the collapsed objects such as galaxies and stars or planets, all the structures we see in the present universe. Okay, so this is a basic picture of the evolution of the universe. Now, let me briefly explain what a primordial black hole is. So primordial black holes are black holes formed in the very, very early universe when the universe was still filled with hot radiation. So this shows a schematic picture of the inhomogeneity of the energy density of radiation. And the radiation consists of photons, quarks, or leptons, any relativistic particles. And we usually define the quantity, which is a relative difference of the energy density. And we call this the primordial density perturbation. And since this primordial density perturbation originate from the quantum fluctuation during inflation, this density perturbation is a random field. And it is known for a long time that if this density perturbation, amplitude of the density perturbation is greater than some threshold value, which is about 0.8, then this overdense region, the self-gravity defeats the radiation pressure, and this region directly cracks into a black hole. And this black hole, since those black holes are produced in the primordial universe, those black holes are called the primordial black holes. And we can estimate the mass of the resultant primordial black holes by this formula. So the black hole mass is related to the wave number of the perturbations. And if the moving wave number is about 1 parsec inverse, then the mass of the black hole is about 10 solar mass. And here I explain some properties, basic properties of the primordial black holes. And contrary to the astrophysical black holes, which are formed from the collapse of the stars, the astrophysical black holes are believed to be heavier than 1 solar mass. And contrary to these astrophysical black holes, primordial black holes with any mass can be produced in the early universe. So this is the same formula as I showed in the previous slide. So the PBH mass is related to the wave number of the perturbation. So just by changing the wave number of the perturbations, we can have the primordial black holes much smaller than the solar mass. So this is a very different property from the astrophysical black holes. And another interesting point of the primordial black hole is that it's a candidate of dark matter if the primordial mass of the primordial black hole is greater than about 10 to 15 grams. If the primordial black hole mass is smaller than this value, then such black holes undergoes the Hawking radiation and evaporate by the present time. So they cannot be a dark matter. And another interesting point about PBH is that they may explain the LIGO events. And actually this is the reason why the people recently got interested in primordial black holes. And finally, the PBH abundance is sensitive to the variance of the primordial density perturbation. And the abundance of the primordial black holes can be written by this formula, where P is a probability that the density contrast, probability density for the density contrast. And this is a figure showing the PBH abundance as a function of the typical amplitude of the primordial density perturbation. And as you can see that the PBH abundance is sensitive to the typical amplitude of the primordial perturbation. So given this, the natural question I want to ask is how inhomogeneous was the primordial universe? And on very large scales, I mean the wave numbers smaller than the megaparsec inverse, there are already cosmological measurement of the primordial density perturbations, such as the temperature anisotropy of the cosmic microwave background. But on smaller scales, there are no such measurements. And primordial black holes are relevant to such small scale density perturbations. And by answering this question, we can understand if the primordial black holes are created in the early universe. And another interesting point is that irrespective of whether the primordial black holes are created or not, obtaining the information of the primordial perturbations on the small scales is important from the point of view of the inflation models, because we still do not know the concrete mechanism of inflation, because the inflation energy scale is much higher than the ones accessible by the terrestrial experiments. So we do not know physics of inflation. So getting the information about the primordial density perturbation tells us something about the high energy physics. That's another important point to probe the primordial density perturbations. And this is a current knowledge about the amplitude of the amplitude of the primordial perturbations as a function of the wave number. So the vertical axis is the so-called power spectrum, which is an amplitude square of the primordial density perturbation. And this is a large scale, and this is the right side is a small scales. And on large scales, as I said, the measurement of the cosmic microwave background fix the amplitude of the primordial perturbations. But below this scale, we do not know the magnitude of the primordial perturbation. And there only the upper limit exists. And these upper limits are actually obtained by the non-detection of the primordial black holes. Okay, let me skip this slide. Okay, so up to the previous slide was the introductory part of my talk. So let me now go to the main topic of my talk, which is a gravitational wave as a new probe of primordial density perturbations. So as I said in the previous slide, only the non-detection of the primordial black hole was the only way to probe the primordial density perturbation. But recently, the gravitational waves has been considered as a new powerful probe of the primordial density perturbation. And I'm going to explain this in more detail. So again, I show this schematic picture of the primordial density perturbation, and which was created from inflation. These primordial density perturbations can be thought as the initial conditions of the density perturbation, which evolved afterwards. And since in the primordial universe, the universe is filled with radiation, and this radiation has a pressure, when the age of the universe becomes larger than the sound crossing time, then this density perturbation undergoes the acoustic oscillations due to the radiation pressure, and so this primordial density perturbation becomes a sound wave. And because of this dynamical motion of the density perturbation, the gravitational waves are produced. And since the density perturbation is a random field, the produced gravitational waves becomes the so-called stochastic gravitational wave background. And this fact has been known for a long time. Actually, this fact was pointed out for the first time by Professor Kenji Tomita in 1967. But since the gravitational waves had not been detected for a long time, the people were not interested in this possibility until quite recently. But after the detection of the gravitational waves by LIGO-Varbo collaboration, and also we expect a great progress of the gravitational wave astronomy due to the many planned gravitational wave experiments like Einstein telescope, Cosmic Explorer, and so on. People are now have growing interest in the gravitational waves to probe the primordial density perturbations. And this is a technical part, so you don't need to understand the equations, but this equation just says that this gravitational wave is created by the primordial density perturbation by the so-called second order effect. And because of this, the amplitude of the power spectrum of the gravitational waves is proportional to the square of the power spectrum of the primordial density perturbations. Okay, so given this, we conducted a search for the stochastic gravitational wave background from the primordial density perturbations in LIGO O2 data. And this is a first search by using real LIGO data. And I am very happy. My collaborators are are members of LIGO-Virgo collaboration. And Shasvath Kapadira and Kanhaya Pandi made a great contribution to this work. And I am very happy to be involved in this collaboration. And this is a first search by using real LIGO data. And let me briefly explain how we search the stochastic gravitational wave background. By definition, stochastic gravitational wave background is stochastic. I mean, this produces a random motion in the detector. So the single detector cannot distinguish between noise and the gravitational wave signal. So the idea to detect the stochastic gravitational wave background is to take the correlation between at least two detectors located at different places. And the idea is that the noise produces uncorrelated signals in the two detectors, but since the gravitational waves are coherent, so if gravitational waves exist, the two detectors must detect a coherent noise. This is a basic idea to detect stochastic gravitational waves. And to do that, we consider the cross-correlation statistics, which is defined by this quantity. And this S1 is data of the first detector. For instance, this first LIGO in the Hanford. And the S2 is the detector's data in the Livingstone. And we take the product of two data. And when we take the ensemble average, the ensemble average value of the cross-correlation statistics gives the signal of the stochastic gravitational waves. And this is a variance, which is determined by the level of the noise of each detector. And in order to search for the stochastic gravitational waves, we need to assume the template for the power spectrum. And here we assume the so-called log normal shape for the primordial density perturbation, which is parameterized by 3 parameters, A, sigma, K0. And A represents the amplitude of the power spectrum, and sigma represents the width of the power spectrum. And K0 is a scale of the perturbation we are interested in. And then we construct the likelihood by this standard formula. And for given sigma and K0, we compute the posterior of A. And we repeat this computation over over sigma K0 grid. And after we did this analysis, we did not detect any conclusive gravitational wave signal in the LIGO O2. And by doing this, instead we are able to place an new upper limit on the power spectrum amplitude in the sigma K0 plane, like this. And since, as I said previously, since the PBH abundance is a function of the typical amplitude of the primordial density perturbation, we can transform the upper limit on the amplitude of the power spectrum into the upper limit on the PBH abundance for very small mass range shown here. And this is a upper limit plot for the upper limit on the PBH abundance. And our PBH constraints, interesting point of our research is that our constraints are independent of the assumptions of the Hawking radiation, which is used in the previous study. I mean, the previous constraints consider the effects caused by the high energy particles emitted from the primordial black holes by the Hawking radiation. But this work doesn't assume anything about the Hawking radiation. And since the previous figures like this or this is not easy to understand, so we produced another figure which is easier to understand by choosing a particular value of sigma. So the thick line is a constraint for sigma equals to 0.01, and this dotted, I don't know how to say, dotted curve is the case for sigma equal 5. And these, so let's focus on first, please focus on this sigma equal 5 case. So this is a previous constraint in the literature. And this black one is our new constraint. And you can, and this inset is the so this shows this tiny part, and you can see that these new constraints are stronger than the existing ones, only for a very narrow range of the sigma k0 space. So you may think that the result is not impressive, but I'd like to stress that this is a completely new constraint from the gravitational wave observation. And the gravitational wave astronomy finally started giving us information about the primordial density perturbations. So this is a equivalent constraint in terms of the PBH abundance. And again, our constraints are better than the previous one, only for a narrow range in the parameter space. Okay, so in our analysis, we used live O2 data. And so this is a black, so this is a PBH abundance as a function of the PBH mass. And the black curve is the previous constraint. And the orange one is this constraint from the gravitational wave observations. And the gravitational wave observations, the constraint is better than the previous constraint for some small parameter range. But if we go to O3 or design sensitivity, the constraint becomes much better than the current ones, which shows us the powerfulness of the gravitational wave astronomy in the near future. So it's highly expected that the gravitational wave will become soon the most powerful probe of the primordial density perturbations. This is a main message of my talk. Okay, so this is a summary. Gravitational wave astronomy has started providing useful information about the extremely small scale primordial density perturbation. And we gave the first gravitational wave based constraints on the amplitude of the primordial density perturbations. And we also placed a new upper limit on the ultralight primordial black holes. And that's all. Thank you.
Okay, so thank you very much, Professor Suyama, for this new study on the gravitational waves. So now this floor is open for the questions. We have time for taking few questions. So if you have any questions, please ask.
Can I ask one question?
Yes.
You mentioned that the PBH mask is actually ruled out in the, I mean, you have disfavored it in the range of 5 into 10 to the power 13 to 10 to the power 14 gram in some slide. Yeah. But then towards the last slide, you mentioned ultralight PBH. So they are from the same measurements or very different?
By ultralight primordial black holes, I mean the primordial black holes in this kind of mass range.
Okay, same range. Okay. Oh, you wrote in terms of solar mass in the, okay, fine, yeah.
This is much smaller than the solar mass.
Right, yeah. So they cannot be dark matter, right? This is below the dark matter range.
The primordial black with the primordial black holes, dark matter, the mass of the primordial black holes must be larger than 10 to 15 grams. So yeah, this mass is smaller than the 15 grams. So those
and this, yeah.
But it can be.
And this mass
can it
is
be like
sorry.
part of the dark? Yeah, no, go ahead. Sorry. Yeah, go ahead.
No, yeah, I'm actually done. So I just wanted to know that, yeah. So this mass is at the time of formation, or this mass that you constrain, right? At the time of formation, right?
Yeah.
Not after that.
Yeah, this is a mass at the time of the formation. Yeah.
Right. Yeah.
And if those primordial black holes were actually created in the early universe, they do not exist in the present universe due to the Hawking radiation.
Right, surely.
Nevertheless, we can constrain by using the gravitational wave experiments, we can determine whether such lighter primordial black holes were created or not in the early universe.
Yeah, right. Okay. Thank you.
So, any other question?
Yeah, can I ask, sir?
Yes.
Yeah. So somewhere you have shown that the mass of the primordial black hole versus the primordial density perturbation, and the graph is basically saturating at some point. So why it is saturating?
Can you repeat the question? I couldn't answer.
I mean, you have shown one plot where you have plotted primordial black hole mass or something with the primordial density perturbation.
Which plot is this?
Yeah, please go back. Yeah, this one. Yeah, this is beta is what? I forgot.
You are talking about
yes, this plot. Yes, abundance of PBH.
Yeah. So what's your question?
So why the graph is saturating at some point of the density perturbation?
Why the graph is? I can't.
Saturating. Yeah, basically at some point it is saturating. It is kind of why it is not.
It is becoming constant.
Flat. That is what is.
Yeah.
No, it's not becoming constant. It's increasing, but since this is a log plot, it's not approaching constant.
Okay. Yeah. Okay. Thank you.
Okay, I think let me move on. So if there is no other question, let me thank Professor Suyama for this excellent talk and updates.
Thank you.
So let me move on to the next talk. Fujikura?
Yes.
Fujikura, can you please? Yes. Okay, so the next talk will be by Mr. Kohei Fujikura. The title of the talk is Cosmological Phase Transitions in the Early Universe.
Thank you very much for the introduction. My name is Kohei Fujikura. I'm a PhD student of Professor Masahide Yamaguchi, who is a who research interest rely on the cosmology. And today I would like to talk about the cosmological phase transitions in the early universe. And before the talk, I would like to thank to all of the organizers. Maybe as you can see in the collaborations, there is a Dr. Debashis Boa and also the Deva Pratama Hunter who attend these workshops. And in last year, this work was a part of this work was discussed with Dr. Debashis, and I'm having a really great pleasure to, how to say, connect. I can connect with this kind of great collaborations. So this work is based on this archive number, which is published in the JCAP, and I would like to start here. So this is the introductions. Sorry, this is the contents. First of all, I would like to talk about introductions, which I just say we need a beyond the standard model physics. And after that, as one of the examples, we focused on the models, so-called the scotogenic model. And I would like to, in any case, introduce a scotogenic model and explain what is a model. And after that, I would like to explain what is the implications of the first order electric phase transition realized in the models, and can we really constrain this model by the observation of the gravitational wave generated by these phase transitions or not? So this is the introductions. So this is a matter contents of the standard model of particle physics. As you can see, we have quarks and leptons, and also the gauge, as well as the gauge bosons. And the final pieces of the standard model, which is the Higgs bosons, was discovered in the 2012. And all of the observations around of the electric scale physics are in agreement with the precision test and also the flavour observations. So it looks that at least the standard model of particle physics is a good effective theory which describes the physics around the electric scale. Also, here I would like to say that standard model physics is not the ultimate theory. This implies that this is not a theory of everything, because the standard model cannot explain following phenomena. The one is the dark matter. So in the standard model does not have do not have any dark matter candidate, unfortunately. And also, as we know, we have a non-zero but still tiny neutrino mass for the left-handed tiny neutrino mass. But in the standard model, since there's no mechanism to give a non-zero mass to the neutrino, so it remains massless. So in the standard model framework, we cannot explain neutrino masses. So in any case, I think we need a beyond standard model physics. So as I said, in this talk, I would like, in this work, we focus on the scotogenic models, where in this model, in addition to the standard model particles, additional S2 doublet and also the 3 light-handed neutrinos are introduced in order to explain the dark matter as well as the neutrino masses. So let us look into a more detailed way. So this is the interaction with the standard particles with the additional particles. So if we look at the scalar sector, this is the potential for the standard model Higgs. So this psi denotes the standard model like Higgs doublet. And this shape of the standard Higgs potential is completely same to the standard model 1. In addition to this potential, we introduced another S2 doublet, scalar of the S2 doublet, so-called the inert scalar doublet S. So if we demand the renormalizable interactions as well as the gauge principles, we can write down this kind of possible terms. This is the mass square terms and also the interaction terms and the quartic couplings. And as I said, in this model, the right-handed neutrinos are introduced. So since the right-handed neutrino is singlet under the standard model gauge charges, so we can write down the Majorana mass term for the right-handed neutrinos, and also we can write down the Yukawa coupling with the standard model leptons and the inert scalar and right-handed neutrinos. So if you look at this Lagrangian and also scalar potentials, there is a discrete symmetry, so-called a Zitz symmetry. So this Zitz symmetry is corresponding to the flipped sign of the new particles. So this implies that this kind of discrete symmetries ensures the stability of the new particles. So this implies that a new particle cannot decay into standard model particles. So it's stable, so which can be the dark matter candidate as long as the new particle is not charged under the electromagnetic interactions. So here, as I said, S is doublet, so we can decompose into the 4 real degrees of freedom, like the charged one, and the singlet under the electromagnetic interaction is 0, and H0 can be divided into the CP even component and CP out phases. So H plus component cannot be a dark matter because it is interact via the electromagnetic interaction, but the H0 can be a dark matter. Also, the light-handed neutrino can be also dark matter because it is singlet under the gauge charges. So we have a two scenario. Like if we consider this kind of left one. So this is a line of the mass ordering. If the light-handed neutrinos are lightest, this can be, of course, a dark matter. And also, it is possible to have a scenario where the lightest state is H or A, like a scalar dark matter scenario. In this talk, I would like to consider the deuce scenario in both scenarios, where the fermion and the scalar particles can be a dark matter. Since due to the time limitation, I cannot explain in detail for the generation of the tiny neutrino masses. But as we can see from this figure, in this model, the neutrino mass is left-handed neutrino mass is remain massless, but it can be generated by the loop, this kind of diagram, thanks to the new interactions with the in-atom scalar as well as light-handed neutrinos. So here, let us back to the original questions. So original contents. So here, I would like to talk about electric phase transitions in the realized in the scotogenic model, which is the Biono standard model physics. So here is a slide which describes the first order phase transitions. At the beginning of the universe, as the Professor Suyama-san said, since the universe is fulfilled by the thermal plasma, so the thermal fluctuation plays a very important role. So if you take into account the thermal fluctuation, the Higgs potential is stabilized by the thermal fluctuation, so-called the thermal mass term, and the Higgs standard model Higgs is stabilized by this thermal fluctuation and doesn't occur as wave in the early universe. But due to the cosmic expansions, the temperature of the universe actually decreases and decreases. Then if the, of course, the shape of the potential depends on the temperature. So if the shape of the potential looks like this one, when the temperature decreases and there is an extra minimum, which is separated by a true vacuum and a false vacuum, then the phase transitions with the order parameter is the Higgs wave occurs through the tunneling. So the wave of the Higgs discontinuity change at some certain temperature, so-called the nucleation temperature. So in the position space, this implies that at a very early universe, all of the phase is a symmetric phase. Electric symmetry is not broken, but at a certain temperature, since according to this figure, the Higgs fields tunnels the true vacuum, then the spherical symmetric configuration, so-called a bubble, is nucleated. So first order phase transitions proceeds through these bubble nucleations. In this case, since the departure from the thermal equilibriums, and there are a lot of bubbles are nucleated at the nuclear tension temperature, so which actually collides and breaks the spherical symmetry. So this can be the source of the gravitational waves. And especially, it was pointed out by those authors. There are three sources of the gravitational waves. One of the purely bubble kinetic energy of the collisions of the bubbles, and also the sound wave, which is sourced by, because the bubble kinetic energy can be converted into the thermal plasma due to the interactions. So the compression of the thermal plasma can give rise to the generation of the gravitational waves. And also the plasma effect will give rise to the turbulence of the plasma, which can be the source of the gravitational waves. So recently, the gravitational wave detections is very popular because it is an ongoing space-based interferometer, so-called Resurgent and Aria and Desai and BB wall is designed at around of this frequency regimes. And if you consider electric phase transitions, because the critical temperature is around the electric scale, so this kind of frequency regime will be very important to capture the gravitational wave detection from the first order phase transition. So here's a brief review of the gravitational electric phase transition in the standard model. Within the standard model work, unfortunately, with the observed Higgs mass, it was indicated by the lattice simulation, which is non-perturbative studies. The electric phase transition is not of the first order. However, since if you consider beyond the standard model physics, actually the Higgs potential is affected by the new particle because the Higgs are coupled to the new particles. In our case, photogenic model, this is the S particles. This S particles makes this interaction with the Higgs and the S particles makes the additional barrier of source of the barrier of the potentials, which is needed to realize the first order phase transition. So in the photogenic model, of course, depending on the parameter regime, but if the Higgs and the S particle and the Higgs couples to a little bit strongly, then we can have a first order phase transition. So this is the overview of the calculation method of the gravitational waves. So if we fix a model, we can we know the short distance theory, which is Lagrangians of the model. And after that, as I said, we can compute the effective potential by using the well-established formalism, so-called the Matsubara formalism. And after that, so since we have this kind of potentials, we can calculate the tunneling rate of this given potential shapes. So we can then calculate the relevant parameter, which is the bubble kinetic energy, also the bubble radius from this potential shape. And after that, this is sometimes used in the simulations, but by computing the energy momentum tensor of the bubbles and the thermal plasma, we can put into the right-hand side of the Einstein equation, we can compute the signals of the gravitational waves. So we have a parameter scan in order to study the dynamics of the electric phase transition. We investigate a parameter region which satisfies where the phase transition strength is very strong, so-called the wave of the Higgs is larger than the nucleation temperature. And also for the theoretical reason, we imposing the following condition, which is the perturbative conditions, as well as the vacuum stability and the unitarity conditions, which must be fulfilled in order to have a healthy theories. So this is one of the results of the scalar dark matter case. So the left-hand panel shows the several sensitivity curves of the space interferometers, and right-hand panel corresponds to the this black dotted spots corresponds to the peak of the gravitational signals. And the right-hand panel, we show the corresponding scattering plot for the gravitational signals can be within the ultimate decimal. And this MA and the CP mass of the CP of Higgs and CP of scalar mass of the inert scalars, and this is a charged inert scalar doublet, component of charged scalar doublet, and also that we assume the 100% dark matter in this analysis. So as a color code, we impose, as a color code, we indicate the mass of the dark matter, which is the H of the inert scalar component. Although from this figure, we can say that 100% dark matter can be, we can test it by the 100% dark matter in the scalar dark matter scenario can be tested by the gravitational detection. But also, if we impose the direct detection constraint, what we found is that in the case where the electric phase transition is sufficiently strong, where it is first order, which is a necessity condition of the production of gravitational wave, is a conflict with the direct detection constraints. Because if we make the electric phase transition is of the strong first order, we need a strong coupling, we need a large coupling with the standard model Higgs, which gives rise to the larger cross section of the direct detection constraints. And secondly, but if we consider a fermion dark matter scenario, this is a similar plot for the gravitational wave amplitude and also the scalar mass of the inert scalar doublet. In the case of the fermion dark matter scenario, because fermion dark matter does not couple to the Higgs, so we do not have any direct direction. We do not have strong direct direction constraints. So we can evade this kind of constraint for the fermion dark matter scenario. In that case, on the other hand, we need to care about the lepton flavor violation process because this is one of the examples of the lepton flavor violation process. Because in the standard model case, lepton flavor violation process is generated at one loop, which is suppressed by the tiny neutrino masses. So if we have a lepton flavor violation process in this model, which is the directly a sign of the beyond standard model physics. So if we compute this kind of Feynman diagrams, since every diagram, we have a lepton flavor violation involve the Yukawa couplings, this kind of the lepton flavor violation process can be evaded with a small Yukawa couplings. And so this is a spot of the green spots corresponds to the first order phase transition points, but which is well below of the observed current experimental bound. So in the case of the fermion dark matter scenario, we have 100% dark matter and which can be detected by the ultimate deciders. So this is my summary. So then at the scale and right-hand neutrons are introduced in the scotogenic models. And the first order electric phase transitions realized in the beyond standard physics standard model produce a gravitational wave signals. And in our case, especially in the scotogenic models, gravitational signals within reach of the U deciders with 100% dark matter are almost ruled out by the dark matter direct detection experiments. But in the case of the fermion dark matter scenario, it is still consistent with the current experimental bound of the lepton flavor violation process. Yeah, that's all. Thank you very much.
Okay, thank you. So now we can take one or two questions from the audience. So if you have any questions, please ask. Hello.
Yes.
Any questions?
Yes.
Then maybe can I ask a question?
Yes.
Yes.
Yeah. So you mentioned on the mu UE gamma limit consistency.
Yes.
Did you also look at other, say,
yes,
smoking gun in the
smoking gun
high energy physics like G minus mu on G minus 2 or other, say, hints which could give light to new physics? And are there some consistent things in your model?
Yes. Yeah. In addition, first of all, this is not only the process which gives rise to the lepton flavor violation process. So we have checked all of the other process, which is, and we check that it is still consistent. Yeah. And also in the case of G minus 2, actually we do not calculate, but I think it is cannot be as, how to say, smoking gun of this model.
Mm-hmm.
Yes.
Okay, thank you very much.
Okay, so I think let's this time is up. So let's thank this speaker again, Mr. Fujikawa. So now let's move on to the next talk. Maybe okay. Hello, Reajul, can you share your slide? Can you make a full screen? Yeah.
Yes, is it visible?
Yes. Okay, so now our next speaker is Reajul Haq. So he'll be talking about probing the reheating phase through primordial magnetic field and CMB. Yeah, start.
Okay. Good morning, everyone. Myself, Reajul Haq from Department of Physics, IIT Guwahati. Today I'm going to present one of my ongoing work that probing the reheating phase through primordial magnetic field and CMB. And this work is collaboration with my supervisor, Dr. Debaprasad Maiti. and another PhD student in our group, Saurabh Pal. So basically the motivation that why we try to probe this reheating phase. As you know that reheating is one of the most important early phase of our universe. It essentially links our standard thermal universe with the peak thermal state, such as the inflationary universe, through a complicated nonlinear process. And you know that the cosmic microwave background is crucially depend on the background evolution, starting from this inflation and then from the radiation dominant era to the current era. And so the observe the CMB scale and their horizon exit during inflation must have to correlate it through this reheating phase. So the reheating phase is very important, and only we can put some indirect bound on this reheating phase by this cosmic microwave background. But now in this present work, in addition to that, we also try to probe this reheating dynamics through the evolution of the primordial magnetic field by considering the present value of this primordial magnetic field, the present value of the large scale magnetic field. Okay. So now going to that what we address here, because in this current study we basically consider a present day large scale magnetic field and CMB anisotropy to probe the reheating phase of the universe, followed by the standard inflationary phase. And as you know that in the conventional inflationary magnetization scenario, that after the at the end of the inflation, the magnetic field on the super horizon scale redshift as b squared is proportional to a to the power minus 4 kind of, and the inflated energy density transferred into the plasma instantaneously just after the end of the inflation. But in that case, the problem is that the magnetic field which is produced, the large scale magnetic field produced the present day is not this sufficient. So that's why we actually try to introduce that reheating era, and where it can be shown that if the conductivity remains small redshift during this reheating era, then the magnetic energy density is not redshift as a to the power minus 4, rather than it redshift at a to the power 6 h square. It also shown in this paper, this Kobayashi and Sloth paper. Basically, due to this electromagnetic induction, now the magnetic field changes as a to the power minus 6 h square. And this helps to obtain this required value of the present day large scale magnetic field. So in this work, what you've done, they're taking into account both the CMB anisotropy constraint on the CMB anisotropy and this inflationary magnetogenesis scenario. We can connect among the reheating parameters and the magnetogenesis model parameters through this inflationary spectral index. So now going to the inflationary magnetogenesis scenario, that how we calculate this the electromagnetic power spectrum. So the background of this, if you had this well known the FLRW metric, where the scale factor is time dependent, and it can be expressed by metric expressed by this equation, and now this simple magnetogenesis scenario, which one can think of the well known the scale gauge field model. With the following interaction Lagrangian I square FF kind of Lagrangian, which is basically the well-known Ratra model. And in this interaction Lagrangian, the conformal symmetry is explicitly broken by the scalar field coupling function, because now the scalar field coupling function I is basically a function of phi in the gauge field sector. And the action is kind of given by this equation. And now, in order to quantize the field component mu, that can be expressed in terms of the irreducible scalar and the vector components by this equation, and we can write this VI in terms of the creation and the annihilation operators. After that, if we use the standard commutation relations between the creation and nature operators and the relations between the polarization vector, we can find out the mode function solution, that's basically given by this equation. So if we calculate now the electromagnetic power spectra in terms of this mode function, which turns out by this equation, the peak and PV. After that, if we calculate the Hamiltonian in terms of this time-dependent creation and operator, you can see that this is not diagonal. And so in order to diagonalize, we basically introduce the Bogoliubov transformation, the new creation and annihilation operator, which is basically now time-dependent. And now this new Bogoliubov coefficient in terms of this old creation and annihilation operator given by this relation, and these Wkv coefficients are defined by this equation. So this is the final form of the electric and the magnetic power spectrum in terms of these Wkv coefficient. Now after that, we try to modeling this coupling function, and in order to modeling this coupling function, we basically consider the widely considered power law form of the coupling function, which is basically I is proportional to a to the power minus n during this inflation, and after the end of the inflation, the Maxwell's the standard Maxwell equation is recovered. So we consider it as 1 after end of the inflation. Now if we solve now by considering this mode function, by considering the standard the d theta background, that Hubble parameter is constant during this inflation, so the solution of the UK can be written by this Hankel function. Okay. Now after that, we can define the Wkv coefficient in terms of this Hankel function, and in the super horizon limit, when k is very less than h, this phase parameter theta k, which is basically defined as argument of the alpha k beta k star, and the 1 over beta k square, the beta k square is basically the photon density or number density, is very less than 1, and into that limit we get a simplified form of the electromagnetic power spectrum. And this is the final expression by considering any general values of it. It can be integer, non-integer, anything. And for considering this n being a positive integer, it turns out by this equation, the simplest form. Okay, now go to the next phase, that during reheating era, what happened? But now during this reheating era, this mode function solution can be given by this equation, this UK. And now if we calculate the phase parameter during inflation, now we get an extra term, the 2k time minus tau end. And by this term basically gives the redshift, modified the redshift as the a to the power minus 6 h square. So now the during reheating era, these electromagnetic and the magnetic field is not redshift as a to the power minus 4, now redshift as a to the power minus 6 h to the power minus 2. Okay, and we already defined all the standard relation. From the standard relation, we can define the magnetic spot spectra, this PVK relation during reheating. And then I consider the fact that after the end of the reheating, the conductivity becomes very large. So electric field dies out fast, and the Coulomb magnetic field freezes. And we can correlate this magnetic field at the end of the reheating with the present value by this relation. Okay, and this relation for turns out on a simplistic form for integer values of it. Okay, this is the relation for the integer values of it. In is basically the coupling function parameter, which is already defined here. That well, one second here. This side. Okay. 1 second. Okay. Now go to the reheating dynamics, that how we connect this reheating and the primordial magnetic field. So in order to connect this reheating dynamics with the primordial magnetic field, we basically consider the two different kind of reheating model. First of all, one reheating dynamics, which is the standard reheating dynamics given by Kaminkowski, that the inflator energy density is assumed to be converted into radiation instantaneously just after the end of the at a certain time at the end of the reheating, and this whole phase is parameterized by 3 parameters. One is the effective equation of state, another one is the reheating temperature, and the duration NRE. Okay. And the standard expression for TRE NRE is given by this equation. And now by using this expression where age is now can be correlated with the Hubble parameter at the end of the inflation, we can find out the relation of the phase parameter and the present magnetic field also. Okay, and the ratio of this A0 and AARE is basically find out by considering the entropy conservation. They consider the fact that after the end of the reheating, the combined entropy density is conserved till now. So we can correlate that A0 and ARE in that way. Now in the second case, second reheating scenario, we consider the perturbative reheating model. And what is that? In the perturbative reheating model, we basically consider the effective equation of state is now basically the time dependent. And the perturbative reheating is personally satisfy the standard Boltzmann's equation, these two equations. And here the inflaton energy density, inflaton is decays into the radiation with a constant decay with gamma phi, and the omega phi 1 is the equation of state, inflaton equation of state. And the initial condition is set by the end of the inflation. That end of the inflation, the radiation energy density is 0, but the inflaton energy density is basically 3/2 Pn. This comes out by considering the fact that epsilon is the total parameter 1 after the end of the inflation. Now going to how we define this reheating temperature here. So the reheating dynamics is actually defined here. The reheating dynamics the end of the reheating is defined here at the point when the maximum inflaton energy is transferred into the radiation that they consider satisfied, but H is equal to this is gamma phi, this relation. And the other thing you know that the reheating temperature in terms of radiation temperature, this is the standard relations, and the another relation is from the entropy conservation. That how we connect that present CMB temperature with the reheating temperature. So after connecting all those equations, we can establish one-to-one correspondence between this TRE and the gamma phi. And now in order to connect the reheating and primordial magnetic field parameter, now these phase parameters depend on the evolution of these two energy components during reheating, this rho phi and rho r, how it evolved with respect to time. And the magnetic field power spectrum in the present universe can be find out by this relation. Where this contribution with the term contributions come from this reheating phase, and these actually modified the present value of the magnetic field. Okay, so now going to a short discussion about the strong coupling and the back reaction problem. Because in order to generate the large scale magnetic field required state, the conventional magnetic scenario face either the strong coupling or the back reaction problem. And here in our if we consider in our case, we consider that I is proportional to a to the power minus n kind, and if n is negative, then the effective electromagnetic coupling, which is defined by this relation alpha over I, it starts from a very large value, which actually creates strong coupling problem. So to overcome this problem, we consider that n is greater than equal to 0 in our analysis. Well, here is another problem. Arise due to the production of the electromagnetic energy when take over the background energy density, which is defined as the back reaction problem. So to avoid this back reaction problem, this condition must be satisfied that the rho A over rho total must be less than equals to gamma. Okay, and less than equals to the curvature perturbation value tau is then identified as the another quantity, the curvature perturbation, and its value is near about 10 to the power minus 5, I think, from the Planck result. And for the integer values of it, and this condition turns out in this relation. And in our analysis, you can see if we consider either the electric power spectra, the scale invariant electric power spectra, or the scale invariant magnetic power spectrum, in the both case, we avoided the strong coupling and the back reaction problem. So going to our results. So first of all, these results are for the scale invariant electric power spectra, which for n is equal to 2, the n is equal to 2 model basically generates the scale invariant electric power spectra. And the for electric spectra, here I plotted the reheating temperature as a function of ns in the first plot for different values of the present magnetic field. The second plot is the same, but only we've tried to see the variation of the effective equation of state during reheating with respect to the scale factor. And third plot is for the variation of the magnetic field, present magnetic field with a variation of effective equation of state for center values of spectral index. And all result we have done, these three plots are done for the case 1 case, where the full reheating dynamics is determined by an identified by an effective equation of state. And for numerical purposes, we consider 3 different kinds of inflationary models. One is the Higgs inflationary model, already the potential is shown here, and the minimal Plateau model. And in case of minimal Plateau model, we consider the phi star equals to the 0.01 Planck mass. and another one for natural inflation model. The last plot here is for the perturbative analysis. For the perturbative analysis, we can see that perturbative analysis, the strong magnetic, the magnetic field is not within the observation range, because the observation range is 10 to the minus 9 to 10 to the minus 22. So it is failed to produce the sufficient amount of magnetic field. But all the case one, but in the all the case one scenario, the effective equation of state lies within this value 0.150 to 0.325. Here you already mentioned this result, that for the case one heating scenario, irrespective of the model answer under consideration, the large scale magnetic field constrain the effective equation of state within this range, and we predict the low reheating, always predict the low reheating temperature for scale in electric field, which is around 10 to the power minus 2, is which is the BBN, and to the 10 to 10 cube 1 TeV temperature. And for all reheating scenario, there exists a maximum reheating temperature which is around 1 TeV. But for the perturbative reheating model, we found that that it is not within the observational limit. Quick go to the result for the scale invariant magnetic source vector. The all plots are same, only the difference is that here we have plotted for scale invariant magnetic source vector. Here the coupling this function parameter, the n equals 3 here. And here we can see this n is equal to 3 model is always predict the stronger magnetic field, because here we can see the magnetic field of the order of 10 to the power minus 9, 12, 15 in that range. And another thing is that that unlike n is equal to 3, the n equal to 2, the n is equal to 3 model is predict the reheating temperature from ranges from 10 to the minus 2 to BBN to the 10 to the power 15 GeV, which is corresponding to the instantaneous reheating case, and without any back reaction problem, which was the main concern in the inflation mechanism scenario. Okay, and another thing I have to mention that now in that scale invariant magnetic source vector scenario, the equation of state varies from -1/3 to 1/3, so it can be any value. So the scale invariant electric source vector case is constraining the reheating dynamics more than this magnetic source vector. So that's also what we have just the main motivation of this work is to predict the unique value of the effective equation of state with a specific choice of the present magnetic field. Okay, and by taking into account both the CMB constant and the reheating phase, we can uniquely probe the evolution of the primordial magnetic field. Yeah. Okay, thank you, Vivian. That's all.
Okay, so thank you for this talk. So any questions? One quick questions for him.
Can I ask one question? The Riazul, so that natural inflation that you have discussed, is it still allowed? I thought the minimal natural inflation gave rise to a large NS. Yeah, this potential, is it still allowed?
It is allowed. It is allowed for F equal to 10 to 50 Planck mass range. It is within the Planck 1 sigma limit.
So the correct value of R and NS you can generate.
Correct value of R and NS. R values is quite large. It is near about 0.064, but it can.
Still allowed.
Still allowed.
It's just, I think, marginally at the boundary of this.
Yeah, that's what I heard. Yeah. Okay.
Marginally.
Fine.
Okay, I think let us move on. Thanks, Riazul, for this talk.
Okay, thank you.
Now let us move on to the last section, last talk of this session and also of this the whole workshop. Professor Shantobruta Das, can you please share the slide? Hello? Yes. Okay, so now the last talk will be given by Professor Shantobruta Das. The title of the talk is Probing the Effect of Strong Gravity in Black Hole X-ray Binaries.
লিস্ট ওকে ঠিক আছে ঠিক
Rajul, mute your microphone.
Depu, am I audible?
Yes, you are audible. It is visible. Yes.
Okay. So it's really encouraging fact that I'm giving the concluding talk. I'll talk about probing the effect of strong gravity in black hole X-ray binaries. So these are my collaborator for the work that I'm going to present. Some of these Indu is was my graduate student. He just got the degree this year. Debu is here. Shayan is also from IIT Guwahati, and Anuj is from ISRO Bangalore, and Shomir from IIST Trivandrum. So the roadmap to decode the black hole gravity is the following, with a very simple-minded words. The black holes are the most simplest object in the cosmological sense, because it can be characterized by their mass and spin. And by definition, black holes are literally black, and because of that, we cannot directly observe them. So the observation of black hole means that we have to rely on some indirect means. What does it tell us? It's that because of the strong gravity, black hole attracts surrounding matters onto it. And this process is essentially called as the accretion process. And when the infalling matter is falling towards the black hole, its acquired gravitational potential energy is converted to the thermal energy, and therefore it becomes hot, and it emits electromagnetic radiations. And that electromagnetic radiations essentially carry the telltale signature of the black hole's strong gravity. So by analyzing these electromagnetic radiations that are supposed to come from the ambient medium around the black hole would be a key features to detect the black hole, astrophysical black holes. So this is an artist view of a typical accretion process when there is a binary system. One star is a secondary star, which is supplying matter to the primary black hole stars. You can see with the arrows, the typical positions are indicated. Once the secondary stars are supplying matter to the primary, it's because of the strong gravity, it strips away towards the black hole, and it forms a disc-like structure. It's because of the angular momentum present in the matter. Now, in the entire process follows certain boundary conditions. These simple boundary conditions are as follows. When the matter is coming from far away from the black hole, the flow velocity is essentially subsonic. What do you mean by subsonic is the typical velocity is very, very small compared to the local sound speed. And at the horizon, where Rg is denoted the Schwarzschild radius, at the horizon, the matter velocity, the flow velocity would be of the order of the speed of light. That means the characteristics of the velocity would be supersonic. That means it is very, very large than the local sound speed. So these two considerations tells us the accretion onto black hole must be necessarily transonic, and the location where the smooth transition from the subsonic region to the supersonic region happens, it's essentially called as the critical point. So the existence of a critical point in black hole accretion is very, very essential. Now, this is the information is in our hand, and with this, we try to model the accretion flow like this. If we look at a very small region around the black holes, typically the length scale is about 10 to the power 4 to 10 to the power 5 Schwarzschild radius. The simple the accretion disk model looks like this. So here you can see the black hole is sitting at the center, and there is a accretion disk. The cross section is the meridional cross section you can think of, and the direction of R is the direction of the equatorial plane, if you can imagine an equatorial plane in the accretion disk, and Z is the direction perpendicular to that equatorial plane. So this is the simple geometry of the accretion flow around the black hole. And with this geometry, if we study the flow property, means how the flow is behaving while falling towards the black hole, considering a Newtonian star, if you consider the black hole is a Newtonian star, then what happens? Its phase space portrait becomes like this. Phase space portrait in the sense, we are familiar with phase space portrait for the particle dynamics, but in the fluid dynamics, it is something like a variation of Mach number. Mach number is essentially the ratio of local velocity, radial velocity over sound speed, which we have plotted in the y-axis as a function of the radial coordinate. Black hole is sitting somewhere here. Now you can see that flow is coming subsonically. This region is a subsonic region from the very far away from the black hole. Arrow is the direction that indicates how flow is moving, and R out is the outer critical point. The definition of the critical point I just mentioned, where the flow makes a smooth sonic transition, and it becomes subsonic. But you see, the flow cannot go to the black hole if it is a Newtonian star. So its trajectory is closed, it cannot fall into it. Now, what is important thing is, if we consider the general relativistic accretion flow instead of if we treat black hole as a general relativistic object rather than a Newtonian star, the scenario changes dramatically. So what we get a variety of solutions. I will briefly describe what is the meaning of this plot. So in this plot, you can see there are several panels, altogether 7 panels, all are depicting different kinds of accretion solutions when their input parameters are taken from different regions of the parameter space spanned by the angular momentum along the x-axis and energy along the y-axis. So you can see that in this plot, there are certain interesting things you can identify, which was missing in the case of a Newtonian star, that is the existence of inner critical point. Now, if you look at the panel marked as A, which is essentially a solution, you can get it from the parameter space from here. Here, both the outer critical point as well as the inner critical point is present. And this presence of the inner critical point is the signature of the general relativistic features, which was absent in the Newtonian case. Now, if it is the case, then what interesting things we can get it from here? Let's take up the accretion solution marked A. And here, if we study the flow features in the right-hand side that we have showed as a phase space portrait, the flow is coming subsonically from the outer edge. It crosses the outer critical point marked as R out towards the right, and it continues to go in towards the black hole following that arrow trajectory. Now, after a certain point, you can see a vertical jump, which is essentially termed as the shock transition, and it jumps into the subsonic branch again, and is gradually it picks up its velocity, and again it passes through the inner critical point marked as R in, and finally it goes into the black hole. Now the question is why there is a shock transition, particularly when there is a possibility that flow after passing through the outer critical point can smoothly pass through the outer critical point and smoothly go into the black holes, which is indicated by the broken lines, and why flow did not choose that path. The answer is the following. Particularly, shock happens for in the astrophysical contents quite often when there is a possibility of transition from a subsonic domain, supersonic domain to a subsonic domain. So essentially what happens, so the accretion process is the competition between the two different forces which acts in the opposite direction. One is the gravitational force, another is the centrifugal force. So if you compare these two forces in the environment of the accretion disk around the black hole, and here you can see that the blue curve is essentially representing the gravity force, which is expressed as in the right hand side, Here, for simplicity, we are plotting the pseudo potentials instead of the real gravity effect. And the red lines are it's representing the centrifugal force, or lambda is the angular momentum. I mean, this plot is done for a fixed angular momentum. Now, if you look at very carefully this plot in the left-hand side, the gravity force always wins when the R is very large or R is very small. That means very close to the black hole, gravity is important over, gravity is dominant over centrifugal force. And at the very far away, again, gravity is dominant over centrifugal force. But what happens at the intermediate regions, in the intermediate regions, these two forces are comparable. So what happens, you imagine that the flow is supersonic, the gravity force and the centrifugal force is comparable. That essentially means that the flow, even if it is coming with a supersonic speed, feels some barrier that do not allow flow to move inside the black hole, towards the black hole. So there will be a continuous accumulation of matter just because the velocity is being slowed down. And once this accumulation of matter happens, so this accumulation of matter generally do not continue forever. There is a limiting threshold. So if slowing down of the inner part of the disk is reached some threshold point, it creates an effective boundary layer and a discontinuous transition forms, which is called the shock transitions. So in the right hand side, you can see a cartoon picture or cartoon model, you can say it's a toy model, you can say, where there is a disk and at the inner part, there is a torus-like structure, which is the byproduct of the shock transitions, because due to the shock transition, the density as well as the temperature of the flow is increased suddenly, and it creates a torus-like structure around it, which is essentially act as an effective boundary layer around the black hole. And this we call the post-shock corona. Now, this post-shock corona region is containing a very large number of high temperature electrons. And that electrons has a certain role to play. I will explain you in details after some time. Now, the question is, this kind of shock transition is preferable once it is dynamically allowed. Means, if you see that the shock solutions are containing a higher entropy content, then the shock solutions are preferred. So what is the supportive features of it? If you look at the left side figure, you can see that is the accretion solutions is presented. It first passed through the outer critical point X out, and it was supposed to pass through, go through following the dotted line, but it didn't. It makes a discontinuous dump to the subsonic branch, and after that, it again passed through the inner critical point marked as X in, and ultimately it falls into the black hole. Now, if you look at the lower panel of the left-hand side figure, we have plotted the entropy content, and you see the entropy content of the solution, which is passing through the inner critical point, which is larger. So nature essentially accepts the higher entropy solutions, and therefore the shock solutions are always preferred when it is dynamically possible. So this is the theoretical understanding. Now, from the numerical simulation side, there are some support. Support is the following. So this is a numerical simulations of the accretion disk of size about say 400 Schwarzschild radius. This simulation was done in a spherical coordinate. Now you can see that the flow is injected from the 400 Schwarzschild radius, and it falls into the black hole, and it simply and it forms a nice shock structure around it, typically around the location around 100 Schwarzschild radius or so. So this is a one solutions, and here the color map is indicating the density scales. As I pointed out, in the post-shock region, the density is higher compared to the post-shock regions, sorry, the p-shock regions, and it is clearly visible from here. And in another simulation, here you can see only the first quadrant. The flow is injected from around 50 Schwarzschild radius with certain height, about let's say 25 or so. And again, you can see that the shock forms around 10 to 15 Schwarzschild radius length scale, and the post-shock regions become extremely dense compared to the pre-shock regions. So this is the numerical support from this idea. And in a similar context, I mean, we have seen the existence of shock waves in supernova. Yesterday, Shobhan talked about the supernova explosion while explaining the neutrinos, neutrino properties, and mentioned about the existence of shock. And in fact, the bow shock, it is visible ahead of the moving stars in Kappa Cassiopeia. For example, the shocks in some astrophysical jets in HS34, you can see all the shocks scenarios are commonly seen. So the shocks in accretion disks seems to be a viable ingredient. Now, with this, what we can extract, what important physics we can extract so that we can make some remark about the black hole features. Now, the usefulness of the shock study is the following. In the left-hand side, we showed a typical phase space portrait in the upper panel, where you can see how the Mach number is varied as a function of radial coordinate. And this is shock-induced solutions. And the lower panel, it shows the typical temperature profile for electron and the ion inside the accretion disks and inside the shock accretion disks. Now you see close to the black hole, towards the inner part of the disk, let's say the shock is happening here about just above 100 Schwarzschild radius or so, the electron temperature is sufficiently high. It's above, it's more than 10 to the power 10 kV or so, Kelvin or so. So at this high temperature, what happens? The inner part of the disk, that's the torus-like structure we usually call the post-shock region, there is a huge number of hot electrons available. Now the low energy photons, which are essentially coming out in all possible directions, almost isotropically from the outer edge, because their temperature is sufficiently low, so they are supposed to emit low energy photons. Some of these low energy photons must intercept by the effective boundary layer, the post-shock corona, and there they will generate the hard photons just following the inverse Compton process. So the low energy photons, when it is interacting with the hot electrons, the low energy photons is gaining energy from the electrons. So electrons becomes cooled down and the hard radiations are coming out, which we essentially see using our satellites. Now, this is the typical procedure, the way we can expect the hard radiations in the form of X-rays. And what is the utility of it? In the right-hand panel, you see there is a simulation result I also showed earlier. The shock locations, which is you can see around it is oscillating around 10 to 20 Schwarzschild radius. That means the post-shock regions, which is the source of the hot electron, this one is not a steady features. It is essentially oscillating just like a bellow action. Okay. So if the source of the hot electron is executing a modulation of the inner part of the disk, so it is expected that the emitting hard radiations, this will also be coming out towards us in a aperiodic fashion. So that aperiodicity we can estimate from the theoretical findings, which is essentially something like an inverse of the aperiodic frequency we can estimate just by calculating the infall time scale, and in the post-shock regions, within the post-shock corona, and this is the typical relations we can very easily calculate by considering the shock properties like compression ratio and the shock location. In the mathematical expression, the capital R represents the shock compression ratio, which is essentially the measure of the density compression, the how much amount of density is being compressed due to the shock transition. That is the measure of it. And RS is the shock locations. Now these relations, if we use in our theoretical modeling, we can estimate how the QPO frequency, the frequency which essentially can be calculated just because of the shock oscillation, the shock front oscillations. This is the plot here. So in the x-axis, we plot the shock location. In the y-axis, we plot the compression ratio. And the right-hand part, the color bar is indicating the QPO frequency variation in terms of the black hole mass. Now you can see that this calculation is done for an extremely rotating black hole of spin parameters 0.99. And you can see the spin frequency, this quasi-periodic frequency value is ranging from few hertz to about 1,000 hertz or something. So keep taking information from here, we try to address some observational features, and for that we take the use of Indian dedicated astrosat mission. This astrosat mission has a capability of multi-wavelength observations starting from UV to X-rays, and typically this satellite is orbiting once in 90 minutes around Earth. So per day it is making about 16 times, it rotates around us 16 times per day. And for that we choose a particular black hole source named as GRS 1915-105. The importance of this source is, since its detection, this is the most studied black hole X-ray binary source because it's extremely dynamic. If you look at the publication ratio, since its detection, it's close to 600 publications in the refereed journal is already there till today. So what we did, the GRS source is being observed by Astrosat during 11 to 15 July 2016. And in this observation, we have 100 kilosecond guaranteed time data that we have analyzed. In this analysis, we have taken only the X-ray data from the two different instruments. One is the imaging instrument SXT, which operates between 0.5 kV to 3 kV, and the proportional counter instrument LAX PC, which operates between 3 to 80 kV or something. So these data, when we analyze for the light curve, which is essentially the indicator of how the number of photons is varying with respect to the time. Now in the upper panel, it is for one particular orbit. In the lower panel, it is for another particular orbit. These are the photon variation with respect to time. The inside panels, they are the color diagram. I'm not going into the details of it. So if we take the Fourier transformation of these light curve, what for one particular orbit, what we get, it's a power density spectra like this. Now, if you carefully look at this power density spectra, towards the right-hand side, there is a sharp peak is happening in a very narrow range. This is the signature of the high frequency QPO for this particular for this black hole source, which is being observed by Astrosat mission, and that QPO frequency is obtained is around 67 to 70 hertz range for different observations. And what is more, we get that these high frequency QPO, I mean, here just to point out that these important features are happening in the typically several tens of frequency range. So next onwards, whatever result we will show the frequency range between 20 to 200 hertz range. Now you can see in the different orbits, sometimes this QPO frequency present and sometimes this QPO frequency is absent. And these orbit numbers is, you can see it is sequential. It's the difference of a day or something. That means this particular source is very, very dynamic in nature. And this thing is, this calculation, power density spectrum calculation is done for the energy range of, for this photons of energy range 3 to 25 kV. What is more, we have seen here when for a particular orbit, we see the what kind of photons having certain range of energies participating for these QPOs. We see that the QPOs are only being seen when the photon energy of these radiations are ranging between 6 to 25 keV. If the photon energy is less than 6 keV or greater than 25 keV, we did not find any QPO features. That means that particular range of photon which is participating in the QPO features is very important for us to decode what is happening towards the black hole, because high frequency QPO is possible when the modulation is happening very close to the black hole. That's why it is giving the high frequency QPOs. So keeping this thing in mind, we did the spectral analysis of this particular source again, and we have done the unfolded energy spectra fitting using using a particular model. It's a non-thermal component model and the power law component model, which is additive in nature, and we got the best fit. And from here, what we get, up to this energy range, the data is fitted very well for the non-thermal component model. That means the physical explanation that we have given for the inverse quantization process. But above the energy 25 keV, certain extra power law features are required, which is possibly the signature of another post-shock region very close to the black. So that means the non-thermal component that we have discussed earlier, that these are the photons which are participating in the QPO features. Next onward, we have done the spectral analysis for different orbits considering different models. Why different models compared to the earlier one? Because the earlier model was the non-thermal models which could not give us the physical parameter extraction of the black holes. But here we use the simple and the CARBB model, which has the power to give the to extract the physical models. So in the left-hand side, we have fitted the GRS spectra for orbit 3841, and the right-hand side we have done the spectral fitting for orbit 3860. In both the cases, we got the best fit model using the broadband spectral modeling parameters, which is this. It's a slightly complicated model. It's not the additive model. And from here, what physical parameter that we extracted, it is the following. So altogether, we have done 4 different analyses for the spectral modeling using this particular model parameters, particular spectral modeling, and we extracted the parameters like this. What is interesting here towards the black hole parameters, so we in all the cases, all 4 different fitting, we get the black hole mass in the range of these towards the higher side in terms of the X-ray binary sources. It's of the order of 12 solar mass or so. And also we estimated their spin values of this particular source, which is in the range of 0.09 and above, which is essentially giving us the indication that this particular black hole is an extremely rotating black hole. At the same time, another important information we have extracted for this particular source, which is the accretion rate. We see that the accretion rate for this source is also quite high, and it's typically the accretion rate is more than the 1810 accretion rate. So these are the important physical parameters we can extract from this particular black hole source. And this essentially the indicator of these X-ray binaries that this is a black hole having a very strong gravitational signatures. So with this, I think I'm close to the time. This is the summary. Summary is the following, that the shock-induced accretion solutions can decode the signature of black hole strong gravity. QPO phenomena could be due to the modulation of the shock oscillations, and more most importantly, what we want to emphasize here, that we have pointed out that the GRS 19105, this is a very well-studied galactic X-ray binary sources, which is we have found that it is maximally rotating and its mass is towards the higher side in the family of X-ray binary sources, and it is accreting in a very high accretion rate. It's above the super Eddington rate, and also it exhibiting high frequency QPO. Typically, this kind of features, high frequency QPO features, are not very common for high mass X-ray binaries or altogether X-ray binary sources. And towards the end, we must point out that this is the first time we have concurrently studied the mass, spin, accretion rate, and the high frequency QPOs of this particular source, GRS 1915105. For the first time we have done it, and we have done it using the Indian Space Mission's AstroSat observations. So this is all. Thank you very much. I'd be happy to answer any questions.
Okay, thank you, Professor Das. So I think maybe I can take one or two very quick questions. If anyone has any questions, please ask. Any questions?
I have a question. This is Nobuyuki Kawai.
Yes.
So the high frequency QPO, you suggest it's the caused by the standing shock?
No. Standing shocks, I mean, by definition, it is standing. It cannot produce high frequency QPOs. So what we are suggesting is, so if standing shocks are the indicator for the shock transition, then for some analysis, particularly in the simulation result, you have seen that if you carefully choose the input parameters, it can exhibit oscillation, shock front oscillations. Now, if the shock front oscillations can be, the time scale can be estimated due to the post-shock infall time scale, so the QPO frequency would be of the order of. It should be proportional to that. So that's why we have estimated the QPO frequency using the information of the standing shock. And we found that it can give rise to a very high frequency as well. So in principle, you are right that standing shock itself cannot give the high frequency QPO. By definition, it cannot.
Okay. Why is the, then how do you explain the QPO is limited to certain energy range?
So essentially what happens, the way we describe the standing shock, so standing shock is present for a certain range of energy, let's say, energy and angular momentum. Now, there is a certain situation where the particular energy range will not give you the standing shock, but it can give the oscillating shock. So once the standing shock solutions disappears, that shock solutions possibly can give rise to high frequency QPOs, provided if it forms very close to the inner critical point.
Yeah, my question is why the QPO is observed only in the certain energy range of X-rays?
Why QPOs are?
Yeah, you showed that the QPO was observed only in the some energy range. You showed.
Okay. Okay, I got your point. So your point is, in one case in the PDS plot, I have shown that the QPOs are only seen between 6 to 25 keV.
Yeah.
Okay. So
why is that? Why don't you see that in the lower energy range, for example?
The simple reason possibly would be, see, this particular range of energy is essentially the indicator of hard X-ray radiation. So the hard X-ray radiation is only produced provided you have a certain kind of Comptonization happening inside the disk. So if you want to have a Comptonization in the disk, you need a source of hot electrons. And our claim is the source of hot electron possibly due to the shock transitions, because it is naturally happening in that case.
Okay, thank you.
So I hope you recognize me. Last year we met together.
So Santo,
yeah.
Can I ask you? Yeah.
Yes, yes.
So what's the sampling time of data that the power spectral density that you showed? What's the sampling time?
Sampling time means?
Means that what is the interval at which the data were taken?
Well, I think the power density, it is, I think it is a microsecond.
And okay, so that time scale is of the order of the shock observation?
No. Shock observation is nothing to do with this observation. So observation is separate. These observational features we are trying to explain using the shock solutions.
Okay, fine.
Okay, so maybe I think we are running out of time. So maybe with this, I close this particular last academic sessions. And so we thank not only the speakers of this session, we just know all the speakers of the whole workshop. Let us thank. And so now I think I hand over to our HOD and Professor Kazu to discuss about the future course of action.
So, after a successful completion of the second joint workshop between TokyoTech and IIT Guwahati over the last 3 days, now it's my pleasant duty to propose a vote of thanks. So on behalf of the organizing committee, I express my sincere gratitude to Professor T.G. Sitaram, the director of IIT Guwahati, Professor Rakhi Chaturvedi and Professor Rajiv Bhattacharya, respectively, the Dean and the Associate Dean of Alumni Affairs and External Relations, without whose active interest and cooperation, the joint venture would have been very difficult. Also, I take the opportunity to thank Professor K. Yamada, the Dean of School of Sciences in TokyoTech, and Professor H. Tanaka for their words of wisdom and encouragement and helping out the joint workshop in all possible ways. On the organizational part, I sincerely thank Professor Masahiro Kuze, Professor Bhanu Das, Professor Hiroyuki Hirayama, Professor Katsushi Ito, Professor Osamu Jinochi, Professor Susumu Saito, Professor Yusuke Nishida, Professor Takashi Nakamura, who's the Deputy Chair of the Department of Physics at Tokyo Tech, for helping advising, steering the joint conference in each step of the way. On the IIT Guwahati side, I take the privilege to thank Professor Shubhadeep Ghosh, the chair of the Department of Physics, IIT Guwahati, Professor Tapan Mishra and Professor Debashish Bora for a skillful handling of several issues since the inception of conducting this joint workshop, which arose, say, about more than 2 months ago. A technical team comprising of Mr. Basav Purakasta and Mr. Hemanta Medhi was appointed by the chair of the department in order to take care of the technical platform, which later was no longer required owing to the Zoom platform provided by the TokyoTech. And once again, we thank Professor Kuze for offering this platform, which went without an issue throughout the joint workshop. However, their initial involvement of Mr. Purakast and Mr. Medhi are gratefully acknowledged. And finally, as has been mentioned in the inaugural session, that the scientific endeavor shouldn't be inhibited by the ongoing pandemic. I take the opportunity to all the speakers for agreeing to speak at the workshop and interacting with each other. Special thanks are due to the student speaker, Mr. Suman Mandal, Mr. Ayo Hayashi, Mr. Kajal Samanta, Mr. Devabrat Mahanta, Mr. Sota Izumiyama, Mr. Taishi Hata, Mr. Kohei Fuzikara, and Mr. Riazul Haq. Hope I haven't missed anyone. And also I thank all other faculty colleagues at both IIT Guwahati and Tokyo Tech who accepted the invitation as speakers in the workshop, which includes Professor Suichi Murakami, Professor Pankaj Mishra, Professor Girish Setlur, Professor Osamu Jinoshi, Professor Shobhan Chakravarti, Professor Shubhadeep Ghosh, Professor Toru Hirahara, Professor Uday Maiti, Professor Subhash Thota, Professor Takashi Nakamura, Professor Teruaki Suyama, and Professor Shantabhuta Das. So hoping for a third edition of the same to happen with physical presence of all, or either in the online, offline, that's a blended mode next year, as we have already discussed just in the recent past, at either of the venues, and hoping for many more collaborations to open up in the future between the two departments of the two very nice institutions. So with this, I thank all the participants, all the people in the audience, and all the speakers once again. Thank you very much.
Thank you very much, Professor Bass.
Yeah, thank you all. Thank you all for making it a success. Really, we were a bit skeptical that how for 3 days, how it would go, where would be the technicalities, issues, and because the program was really tight, but we pulled it through. And thanks to all your support, everybody who participated in IIT Guwahati and in Tokyo Institute of Technology. So hopefully we will be able to carry forward this to the next level and see you all next year physically.
Yeah, thank you very much, Professor Ghosh.
Yeah, arigatou gozaimasu. And for all these, the video recording of these 3 days are available in the conference web page, so people can visit there and can play the video, watch the talks, and only the talks have been recorded. I mean, for those who had given permission have been recorded. So those are now accessible. The conference photograph is also uploaded in the conference website. So thank you once again. See you. Bye.
Okay, thank you very much. So we can officially close now. Thank you very much.
Yeah.
See you again.
Thank you. Yeah, see you. Bye.
Thank you.
Thank you very much.
Thank you.